Что там самое за движение? В чем проблема?
Исаак Борисович, вы нас видите? Вы нас видите?
Yes.
Разрешить? Разрешаю.
Где камера? Вот есть?
Вот здесь.
Я есть. Вы я делал.
Вот, сейчас это уже свободно. Шар скрин. Безводный шар. Что это? Почему она не слышит? Видите, написано стриминг. Просто. Что он?
Unmute. Okay.
Hello. Good morning.
Good morning. Hello.
Start. Isaac Bersuker, are you ready?
Yes, I'm ready.
Thank you. President of Academy of Science, academicianului, dear colleagues, please let me declare opening of the webinar dedicated of the 95th anniversary of academician Isaac Bersuker. For the beginning, I would propose you to watch the short slideshow, please.
Hello. Okay. Something is going on. Yes. Oh, okay.
Thank you. Next, Elena, next.
Okay. I see you all, but I don't hear you. Okay.
Continue our webinar with academic Bersuker together and together with the quantum science. Who is Isaac Bersuker? Professor Pollinger writes very detailed about him. Yes, thank you. I repeat, Professor Pollinger writes very detailed about him in Wikipedia, and he, I hope, will speak today too. He was born, Isaac Bersuker, born in February 12, 1928 in Chisinau, in the family of the carpenter and the housewife, as one of 4 children. The main field of his research, sorry. The main field of his research concerned the Jahn-Teller effect, which will be developed today in his presentations and to his disciples and colleagues from several countries of the world. Discovery of academician Bersuker was registered as scientific discovery in 1978. The phenomenon of tunnel splitting of energy levels of polyatomic systems in degenerate electronic state. We know that at the beginning of the last century, okay, I would like to use some quantum oddities to explain some nuance of the Isaac Bersuker. In the beginning of the 20th century, scientists made some discoveries that could not be explained. For example, light has been considered as a wave, but light contains particles. Light can transform in particles and vice versa. Good questions. In 1910, when Niels Bohr proposed the planetary model of the atom, it was considered that the nucleus is in the center and the electrons move around it like smaller planets. Later, after the idea appeared that the wave has properties of the particles. Then particles can also have a property of a wave. So the model of the atom is no longer a planet around which other smaller planets revolve, but a more cohesive center in the middle of some valves. It should be mentioned that thanks to this fact. But let's see what happened to Isaac Bersuker. His body, sure. Can he turn into a wave? Yes. I'll tell why. In 1990, he went to Texas, Austin. 2 or 4 times he commuted from Chisinau to Austin. So he has frequency, then he's like a wave. Isaac Bersuker, who are you now? You believe in Austin, not in Chisinau. And you have always been with us. This fact explains Schrödinger black box with the cat. And another thing. And now let's see how quantum science explains Bersuker longevity. How can we turn back the time to look as young as he is? The other day, a month ago, in the quantum chemistry laboratory, we organized a webinar with the academician, 85 years old. Was about the landmarks of the time. And he explained to us that elementary antiparticles turn back in time. For example, positron, the antiparticles of the electron moves from the future to the present, and therefore would allow man to return to to the origin and look young. Isn't right? That's what Bersuker does, being in the horseback and on the electron, he moves forward. When he jumps on the positron, he comes back a little bit and rejuvenates. Sorry? This is some of the quantum what it is successfully used by Isaac Bersuker, which still look very young today, 95 years of biological life and 75 years of scientific activity. And who is the guilty? Schrödinger cat. Okay, just a moment. Where is this program? Yes. And now, if you look the webinar program, we have 9 speakers for our webinar and 2 welcome speakers. I would like to give the word to President of Academy of Science, Academicianului. I propose to moderate this webinar together. Please.
Yeah, thank you, Academician Duca. Ladies and gentlemen, good afternoon in the Republic of Moldova. Good morning in Texas, United States. Good night in Japan. So I am happy to attend this event. Actually, it's a great event, and as Academician Duca said, he is distributed in the space with some probability to find him in Moldova. And now the probability to find Professor Bersuker in the United States is much higher than previously. But the most important is that he actually is always available. And each year he presents lectures here to the Academy, to the Institute of Chemistry in Moldova. And he is an example for all our researchers, an example of devotion. His achievements are impressive, and especially the achievements he has well-known publications, and I got over the last years a series of publications published recently that he's active, and I would like to say very active. To the age of 95 years old, of course, I wish good health to all attendees and to publish papers as Professor Bersuker does. We discussed how we can celebrate the birthday, the 95th anniversary of Professor Bersuker, and the Institute of Chemistry proposed an ingenious way to organize a webinar. At the Presidium of the Academy of Sciences of Moldova, we analyzed all of the distinctions that Professor Bersuker has received, and actually all the Academy's distinctions he already received. But there is one medal Very nice medal, Nicolae Emilescu Spătaru medal. I can show that this is the only one that Professor Bersuker has not received yet. And there was a decision of the Presidium to award him this medal. And Nicolae Emilescu Spătaru, a famous, a great person of our region here, of our country, and he was a great. He lived in the 17th century, passed away at the beginning of 18th century. Was a literary scholar, translator, traveler, geographer, diplomat. I can continue. And I personally consider that academician Professor Bersuker resemble the personality of Nicolae Emilescu Spătaru, in the sense that Nicolae Emilescu Spătaru was our representative in the world, because he was a traveler. He visited Western Europe, Eastern Europe, China, many countries, and was our representative of in other countries. That means a man of at the level of a planet, at the intersection of two centuries, 17th and 18th. Professor Bersuker is a researcher of our country, a representative of our country in other countries, is a researcher of our planet at the intersection of two millennia. And we are very happy to have this possibility to congratulate him with this anniversary, to wish him good health, good mood, and to wish him many happy returns of the day. And of course, we hope to see him again in Moldova or in the United States. It doesn't matter, on our small but beautiful planet. Dear Professor Bersuker, this medal is for you. There is also a document. The document is here. So we will take the opportunity to send the medal and the document to the United States. And here we have a honorary guest, Professor Vasiashta is here, and we will ask him to take the document and the medal with him. And of course, I hope that you will meet in the United States and have the possibility to fix the medal on his coat. Yeah, thank you, dear Professor Vasiashta. La mulți ani, domnule profesor, с днем рождения, many happy returns of the day.
Thank you.
Thank you, Mr. President. Congratulations, Professor Bersuker. And I would like to give the floor to Director of the Institute, Professor Aculina Ricu.
Dear academician Isaac Bersuker, dear President of the Academy of Sciences of Moldova, dear guests, dear colleagues, it is already a tradition at the Institute of Chemistry and calling of the soul to celebrate those who were at the base of the founding of the Institute of Chemistry. And today, on behalf of the team of the Institute of Chemistry, I address myself with a word of greeting to academician Isaac Bersuker. Academician Isaac Bersuker is certainly among the most outstanding personalities who founded new direction in national science, contributed to its development and attestation worldwide. The name of the academician Bersuker is well known in the scientific society and especially in the field of quantum chemistry, both in the Republic of Moldova and far beyond its borders. This fact is due to the achievements that Professor Bersuker personally obtained, and well as by the researchers of the scientific school founded by academician Bersuker, also the results published in prestigious specialized journals from many countries of the world. The international recognition of the high level of research carried out within the scientific school of academician Isaac Bersuker is based on its versatile character, modern and recent conclusions. We are very proud that academician Isaac Bersuker is the only scientist from Moldova whose investigation results in the scientific discovery registered in 1978 in the State Register of the USSR. Academician Isaac Bersuker contributed essentially to the development of the general theory of Jahn-Teller effect, the development of the vibronic theory of ferroelectricity, the quasi-relativistic semi-empirical method for calculating molecular system, and the electron conformational method for forecasting structure-activity relationship, as well as the research of vibronic effect in chemical reactivity and in spectroscopy. Particularly current are Professors Isaac Bersuker researches in the field of coordination chemistry with application of fundamental principle and quantum mechanics for the elucidation of problems regarding chemical reactivity, the electronic structure of reactant molecules, the activated complex and the transition state in catalysis, the modeling of molecular system containing transition metals. Additionally, Professor Isaac Bersuker proposed the use of the so-called computational electron conformational method to identify pharmacophores and forecast bioactivity in pharmaceuticals. In total, Isaac Bersuker is the author of 600 scientific works. Professor Bersuker ideas are continued by numerous disciples, including 50 PhD and 10 doctors of sciences, whom Professor Isaac Bersuker tutored and guided with great care and affection. Among them are Professor Boris Zuckerblad, Veniamin Vechter, Victor Pollinger, Sergei Borsch, Mikhail Kaplan, and others, who are working in different scientific centers in France, Belgium, Spain, USA, Israel, Turkey, and others. Since 1993, academician Isaac Bersuker became a professor at University of Texas at Austin, USA. The appreciation of academician Bersuker achievements by the international scientific community is reflected in the numerous invitation and presentation at conference and symposium, over 150 lecturers and about 40 universities from different countries of the world. Academician Bersuker is member of numerous international scientific societies, a member of the editorial boards and some prestigious scientific journals in the field. Although Academician Bersuker has in the USA for a long time, he maintains permanent ties with the Institute of Chemistry, contributes to obtaining international grants, participates in joint projects, support young scientists by organizing internship abroad, providing consultation, reviewing papers. This anniversary is an occasion to express our gratitude to this talented scientist and organizer of science, Academician Bersuker, the scientist who lives the present, learning from the past and investing in the future. Dear Academician Bersuker, as a sign of appreciation for your prodigious work in the field of chemical science, we would like to grant you the award of the Honorary Diploma of Chemical Society of the Republic of Moldova.
Mm-hmm.
Happy birthday, dear Academician.
Thank you.
Yeah, thank you, the director of the Institute. Ladies and gentlemen, now I would like to give the floor to Professor Bersuker. He will deliver the report, Spontaneous Symmetry Breaking as a Law of Nature. Dear Professor Bersuker, please, you have the floor.
Well, ladies and gentlemen, dear colleagues, thank you very much. Thanks a lot for congratulations, for support, and for the nice words you addressed to me. Let me tell you, 95 years is a lot, but it's not a limit. So let's continue to work, and I hope that our Moldovan Academy in the Institute of Chemistry will organize a webinar again when I will be 100 years old. So I invite you. Okay, now let's see what we can speak about today. But before that, let me also thank especially Academician George Duca, the president, Jahn-Teller, and the director of the Institute, Carolina Ricu, for the nice wording support and the diploma. Thank you. Now, let me see what we have here today is to begin to speak about spontaneous symmetry breaking. But before that, just a couple of words about how I went to science, how I came to science. Well, it's a long story, of course, but just a couple of words. I had a normal primary school for 4 years, and then I was appointed to a school of metal craftsmen. You know, it was a progress in our family because my father was a carpenter, so he was a craftsman in wood. So the progress is that I was intended to be a craftsman in metal. Now, of course, that didn't go through because the World War II began, and then I spent 4 years of field work, not school. And when I come back to Chisinau in 45, I was 70 years old with primary school education, but with a big sensitivity to science, to learning. So what I have done, I began self-invented fast learning. So to be, short, in 2 years, I made through the whole program of the 10 years, and I passed the maturity exam. I passed the university admission exam, and I was admitted to the university. 5 years at the university, that was my real education. After that, of course, it was teaching in different places, with one exception. There's one exception, a happy exception. During my teaching, one of the summer vacations, I went to Leningrad to the famous, to speak with the people of the famous school of Professor Fock, who is an inventor who made the Hartree-Fock method of electronic static calculations. I showed them my university diploma, they liked it, and they invited me for 1 year graduate studies. 1 year, 56, 57, 1 year, exactly 1 year. And I made during this year my PhD on atomic spectroscopy. And I defended my PhD diploma. Then back to Belz, where I was teaching at the Pedagogical Institute. Another happy moment was that I was invited to the Academy of Sciences of Moldova. You see here Professor Ablov, who is a nice scientist and a nice person, and the president of the Academy of Moldova, the first president of Moldova, Joachim Grossel. So they invited me, but it was not so, straightforward. It followed an accident. What accident? In 1959, Khrushchev gave a talk to the United Nations in New York. And during his talk, he stated that all the Soviet Union republics have their own Academy of Science. And he was wrong. And the newspaper liked it because, unfortunately, one of the republics, Moldova, had no Academy of Science. So there was, of course, institutions, several institutions, but not academy. And what happened that next day, Ablov called me and invited me to the academy. There was no academy because there was not enough scientists with, degrees. Now, at the institution, I began a new line of work, and it was related to symmetry. So let me speak about this symmetry problem. First, the definition of symmetry. in science is that symmetry is invariance under transformation. So you make transformations with your system, the transformation of the equations of motion of the system, and it remains unchanged. This is the invariance. Symmetry is very important in science, absolutely important. And it begins, let me give you an authority definition. It was Albert Einstein and his famous work on relativity in 1905. So he stated that it's natural for us to derive the laws of nature and to test their validity by means of the laws of invariance, means of symmetry, rather than to derive the laws of invariance from what we believe is the laws of nature. Now, the symmetry problem was very much discussed. Publications, there's an ocean of publications on symmetry. There are books, especially what quantum mechanics is unthinkable without symmetry, in the books of Wigner, Weil, and others. And there was a series of interesting theorems of Eminator about conservation of properties, and that you have a homogeneous and non-uniform space and time. Symmetry does not be conserved. So this is important things about symmetry. And then my question is, what about symmetry breaking? If symmetry is so important, how do you handle symmetry breaking? Well, you have many kinds of symmetry breaking in nature, but they are mostly induced by some force, by insight, by differences. What about spontaneous symmetry breaking? Yes, there are a lot of spontaneous symmetry breaking in atomic matter under certain conditions. Spontaneous symmetry breaking becomes important because it's inside the laws of matter. Now, Lev Landau was the first to recognize that spontaneous symmetry breaking takes place when you have degeneracy, meaning when you have two or more electronic states that have the same energy. Well, this was verified by Jahn-Teller, and it's known very well as the Jahn-Teller effect. Of course, the idea went out tremendous developments. Now you have many papers, books, thousands of mentions of the Jahn-Teller effect. Now, at next point was the pseudo-Jahn-Teller effect, when you have the same similar spontaneous symmetry breaking when you have not exact degeneracy, but you have closed energy states. Now, this is the pseudo-Jahn-Teller effect. My question at the time was very simple. Degeneracies lead to instability and spontaneous symmetry breaking. What about the question, are the degeneracies the only source of spontaneous symmetry breaking? Or there may be other sources? During the time, not beginning at that time, when I began to work at the Academy, well, we have succeeded to show that yes, degeneracy in atomic matter, degeneracy or pseudo-degeneracy is the only source of instability and distortions. Well, the question is a bit more serious. It's not so simple. You know, you have a global question. Can you have distortions without degeneracy, meaning without at least two states. You know, you have this picture of the Jahn-Teller effect when two energy states in some point coincide and you have degeneracy. So you have instability. This is the Lev-Landau idea. And then you have, when they are close in energy, still you have instability under certain equations and certain conditions. Now, my question was, can you have instability without another state? And the answer is no. You know, the point is, chemists will look on this picture and say, yeah, this is the picture of a chemical reaction. You have the product, you have the reactants in the first minimum, you have the products in the second, and you have the energy barrier. So if this is impossible, so what is possible? So my question is, and my answer is immediately follow this idea that you have to have another, like in the Jahn-Teller effect, you have to have another excited state. You know, there are, you know, even here in the webinar, there will be a presentation about the role of the Jahn-Teller effect in chemical reactions. Okay, now let's see what went on. Why do I say that spontaneous symmetry breaking is a law of nature? So you see, I formulated that you have this two-state paradigm. You need to get instability, spontaneous distortion, you need two states. One state doesn't go, two or more states. So this is the two-state paradigm. Okay, now think about that. Chemists, in order to explain distortions, they introduce hybridization, lone pair repulsion, Wells diagram, anti-aromaticity, steric effects, hyperconjugation. That's all true, but you don't need it if you take into account that the only thing which you need is two electronic states, which are coupled vibronically. So you see, what is going on is that it's a strong statement, okay? But well, we showed that symmetry breaking is why it is going on, and in terms of chemical bonding, we have shown that in the Jahn-Teller effect, the distortion is due because you have better charge distribution during distortion. And in the pseudo-Jahn-Teller effect, you have better covalence bonding. It's more convenient for the system to distort. It gets better covalence bonding than in the undistorted situation. Now, okay, so what I made is some further philosophy. So I have shown that yes, it's the only origin is degeneracy and pseudo-degeneracy. This is in molecular and solid state physics. Now, I was very puzzled to learn at that time that the same idea is true in particle physics. Meaning, you know, the past day you have long ago this formulation. Symmetry breaking is always associated with a degeneracy. In particle physics, degeneracy is about, you know, masses. There's some degeneracies where two particles have the same masses as a degeneracy. So it will have symmetry breaking. So all the transformations and the particle physics are following this symmetry breaking idea, which is associated to degeneracy. So what we have here is all the atomic matter, all the matter in the world. Nature tends to avoid degeneracy and pseudo-degeneracy by means of symmetry breaking. or vice versa. If you have symmetry breaking, it is due to degeneracy and pseudo-degeneracy. Well, then you have what I went further on is to show that all the transformations are due to degeneracy and pseudo-degeneracy. So you go from particle physics to nuclei, from nuclei to atoms, from atoms in gas phase to molecules, from molecules to liquids to crystal. This is when you cool out. So when you cool out the system, you get other kind of degeneracies. One kind of degeneracy gives you a transformation, a symmetry breaking. This is symmetry in the lower part that shows the symmetry breaking. So all the world of matter goes under this transformation. Degeneracy and pseudo-degeneracy controls all the transformations, symmetry breaking in the system if they go spontaneous. Okay, let me distract you. You know, about degeneracy and pseudo-degeneracy in human relations. You know, it was an anecdotal event at an international conference. You know, it was in 2009. It was an international conference in St. Petersburg on coordination chemistry. I had a plenary talk. And in this plenary talk, in order to explain to the people how and why pseudo-degeneracy leads to distortion, leads to instability, I gave them the example. Imagine you have a company, a big company, university, industry, a country, a presidency, whatever. And there were two CEOs appointed, two chief executives with the same functions and responsibilities. Will this situation be stable? People know you will not find in the world such enterprise with two exactly the same functions. So you have a degeneracy in human relations, you know. The point is that it's unstable, it doesn't work. Very soon one of them goes up and the other down, they separate functions and so on. When I said that, there was a applaudissement in the hall and in the audience. Applaudissement, and I was puzzled because it's not usual in scientific conference to applaud. Well, I finished my lecture, and after the lecture, I find out what is the matter. Why applaudissements? Applaudissement, came out that at that time, Putin, the President Putin, he finished his term, and he, in order to make something, that's his idea, he appointed Medvedev as a chief, but he kept all these functions for himself. So you had two chiefs at the time. Two chiefs, you have this, what I call degeneracy. And it didn't last. Very soon one went up and the other went down. And that was the applaudissement. They liked it. The audience liked it. Okay. Now, let me see what we have further on. Okay, degeneracy leads to instability. It's so nice. So what is the practical application of the soul? Innumerable, infinite. Let me show you my fantastic, my first application of the idea. You know, you have some spontaneous symmetry breaking, and you have another physical phenomenon which is called spontaneous polarization of crystals, spontaneous. So my idea was at that time in 64, my idea was, okay, if spontaneous symmetry breaking is always due to degeneracy, that means the spontaneous polarization of the crystal should be due to degeneracy, also to degeneracy. And indeed, I find, yes, that's true. It is, you know, the Jahn-Teller effect is playing this thing. You know, a good example is a very nice crystal, the barium titanate. And spontaneous polarization means titanium goes out of the center, and you have to be all of them. You have an ordering, and you have spontaneous polarization. It's called ferroelectricity. Okay, now this is the case. I will demonstrate you why degeneracy leads to distortion. Look on this crystal. Titanium is in the center of an octahedron of oxygen. And why should titanium go out of the center? Chemists will say, no. Why? Indeed, why? Why is titanium go out of the center? Because of degeneracy. And why degeneracy leads to distortion. So let me show you this example. You see, here in the left-hand side, you have titanium is in the center of the oxygens. It's d orbital, the valence d orbital overlaps with the appropriate combination of oxygen orbitals. But the overlap, plus overlap, and minus overlap compensate each other. So between these orbitals, there's no bonding. However, when titanium goes out of center, you immediately have positive, and with more than negative, you have a non-zero overlap and additional bonding. That's the point. Our degeneracy and the theorems all is this. It is more convenient to get distortion. So you have this distortion. It is more convenient. Everywhere where you have degeneracy or pseudo-degeneracy, you will have distortion because it's more convenient. That is, you know, this very strong word, degeneracy. Nobody's paying attention to this, what degeneracy is, but it's everywhere. It's everywhere and it's very strong. It is very strong, it leads to new properties. Okay, now, of course, this you know, my first application in 64. Imagine, I made it based on my ideas, of course. I was unfortunately single at that time, not only in the Soviet Union, everywhere in the world, I was doing this. The Soviet journals, JET, Central Journal of Soviet Journals, they declined, didn't publish in 64. Then I sent it to the Solid States, the Journal of Solid States. They declined it. Then I made a short note and sent it to an international journal, Physics Letters. They published it. So from 64, I published only 66 because of this declining. And why was it declined? Because at that time, nobody in the Soviet Union knew what is Jahn-Teller effect. Nobody. I was the first to begin it and to continue it. Okay, now let me see more. Of course, this was developed now, and yeah, you know, look on our latest paper on this with Victor Pollinger. You know, just published a year ago or something like that. Unique, it gives this pseudo-Jahn-Teller effect gives you, you know, ferroelectricity in the same crystal, ferroelectricity, multiferroelectricity, permittivity, flex electricity, and polar nanoregions. It is all unusual, and it's all confirmed by experimental data. Now, there are many applications, of course. It's not this place to mention all applications, but well, I have published papers, reviews, and what I show here is 12 from my 15, the covers, 12 from my 15 books. It's funny that, you know, there are half in Russian, half in English, but it's not a repetition, you know. It's not a repetition from one to another. For example, the book on electronic structure of coordination compounds in Russian has 350 pages. The second edition of such a book by Wiley in New York has 800 pages. And the format is a large format, and that is a middle format. Okay, so the books are on electronic structure and on Jahn-Teller effect. With a part of book with Victor Pollinger, with some co-workers. And the first book was published together with Ablov and Kishinev by Știința. Well, let me show you, well, just to mention, because it was mentioned before, about the discovery. Well, what is interesting with this discovery is, yes, not what is written here, maybe, by the way, the discovery was accompanied with a patent, a specialized, not published patent applications. No, so what is interesting? The rules of discovery was that I have to report to the scientific councils of the 10 most important institutions of the Soviet Union. And they have to answer by secret vote. It is a discovery or it's not a discovery. So I went to all these 10 institutions and they all answered, yes, it's a discovery. And that is the diploma. It was in 78, the diploma is from 79 about the discovery. Now, let me tell you, there are many, many applications. It's not the place to speak about the Jahn-Teller, the Jahn-Teller effect. So this is my latest review. By the way, the journal has an impact factor 66. And you can see that there are 3,000, almost 3,000 people who read this paper in the first year of publication. Well, that's all what I want to tell you. Thank you very much for your attention.
Thank you very much, dear professor, for a wonderful lecture. Actually, we enjoyed here in the smaller room, conference room of the Academy, and I hope it was very interesting for all our attendees. I was impressed by the phenomena you touched, and actually very impressive the impact of degeneracy and the example that you gave that two leaders in an office gives to instability. And we can extrapolate this to a family. A family cannot be stable when we have two leaders, both men and women. Women are leaders. That means this leads to instability. Probably. I'm not sure. This should be investigated. Anyway, I would like to ask the attendees from the conference room of the Academy of Sciences of Moldova, and also attendees online, if there are questions, to to Professor Bersuker, please. So, please, Professor Vasiashta.
Professor Bersuker, thank you for the wonderful presentation. Congratulations on all the awards which you received today. Of course, the lecture which you presented is enlightening for me. But I have a simple question. I have worked on piezoelectric materials, and I can see the application of Jahn-Teller effect in piezoelectric materials, which we are using as a sensor for biomedical application. You had mentioned Jahn-Teller's effect, and it's, although I'm saying the same thing, it's application for biological aspect. That was in our private conversation. Could you elaborate on that statement as to what do you foresee application of Jahn-Teller effect for biological types of applications?
Yes, of course, of course. It's a good question. The point is that the Jahn-Teller effect is general, you know, as the degeneracy was what I tried to mention today, that it's general. You have degeneracy, you have to remember the word degeneracy. Well, or pseudo-degeneracy. It's, of course, very important also in biological system. And one of the presentations was today by Dr. Stavrov. He made, when he was in Moldova at the Chisinau Institute, he made applications of the Jahn-Teller effect to hemoglobin. And there are other ones. And our latest publication with Yang Liu in China is about you know, a biological elementary functions. Well, it's, of course, it's general, you know, you have it everywhere. So you have to, it's not applied so far, but definitely in any of these atomic systems, you have electronic states and you have two electronic states, they interact, and then you have this effect. Yes, it's a good question, and that's, the answer is yes. You have it everywhere. Okay.
More specifically, because biological systems, by definition, are statistical in nature, as compared to crystalline structure, where you have symmetry or degeneracy. So I'm trying to correlate in the symmetry and statistical systems, because that's the nature of biological systems. So that sort of pertained to my question, to see if you could, you know, point in that direction for us. Thank
you. Please allow me to intervene. I am Fanica from Bucharest. Please allow me to send my salutation to Professor Bersuker. He was my doctor father. Okay, hello, Professor Bersuker. I am one of the last doctoral pupils of Professor Bersuker in this part of the world. Thank you for making me a doctor and learning about vibronic effects. Of course, vibronic effects are everywhere, but thank you also to Professor Duca for remaking my connection with you. Let me mention that one legitimate place for pseudo Jahn-Teller or two-state effect is the Marcus theory of redox reactions. And considering that Marcus has reached or will reach this year 100 years, I wish also to see your celebration of 100 years. And also let me point another analogy of degeneracy, because I kind of witnessed it. I think that your laboratory in Moldovan Academy exploded because your pupil reached mutual equivalence, and they were quite equal to each other, and then the laboratory distorted and over the whole world.
Thank you. Thank you.
Okay, thank you very much. Are any other questions in the conference room of the Academy? No more questions. In the virtual space, I do not see questions. Thank you very much. Thank you, Professor Bersuker, for this great talk, and we really enjoyed it. And we wish you good health and to continue the impressive scientific activity. We, of course, confirm that we will be present at your 100 years anniversary. Thank you so much, ladies and gentlemen. Then we pass to the next presentation. Professor Pollinger from the University of Washington in Seattle, United States of America. 70 years in pursuit of scientific truth. Professor Pollinger, are you online?
Yes, I am.
Yeah, please, you have the floor.
Thank you. Mr. President, ladies and gentlemen, dear friends and esteemed colleagues, thank you for this great opportunity and honor to present a brief biography of Isaac Bersuker, this extraordinary man who proved and was able to ask right questions, find correct answers, and make right choices in his life. I plan to say something about his early life, his first jobs, his postgraduate school in Leningrad State University, his work in the Institute of Chemistry, creation of the lab of quantum chemistry, something about the American period of his life, and a couple of words in conclusion. Well, let's begin with the early childhood. As we know, Isaac was born in Chisinau 95 years ago on February 12th. That's exactly the time, 95 years ago. Chisinau, as you can see from the map on the left, at that time was a city in the Kingdom of Romania. And the next map shows the map of Chisinau in 1940. Why 1940? It's because that was the year of a bad earthquake, followed by the bombing of Chisinau in 1941, and then in 1944, that actually destroyed the city. Well, you can see that Chisinau was the lower part of it, close to the river Byk, was the old part of the city, and the upper rectangular was the newer part of the city. And the arrow shows the house where Bersukers lived at that time. Chisinau was a vibrant, middle-sized European city at that time, and you can see the picture here. Central Chisinau in 1940, population of about 140,000 people. And to the right, you can see the roofs of the old part of Chisinau, the old side of Chisinau in 1940. Well, a little later, they had to move because in 1941, June 22nd, the World War II came to Chisinau. And well, at that time, the family was had 4 children. One of the 5th child was in the army already. So the head of the family, carpenter, the only working person, decided in a moment that it's time to flee. They took all the, well, each one of these kids took a small bag and they ran to the railway station where they pick up some train going to the east. And they moved. They moved to the north of Caucasus, nearby the small town of Georgievsk, where they were working for about 1 year in a small village as farmers. Then, when German army approached the North Caucasus, they moved to Azerbaijan, also countryside. And Isaac, as other members of the family, were involved in farming. So the following 3 years, he worked hard in a collective farm in kolkhoz for a miserable payment of about 1 kilogram of bread per day, the whole family of 2 adults and 3 kids. The only language of communication was Azerbaijan language, so Isaac learned to speak Azerbaijan. With no school around, he was deprived of the high school education. Well, Bersukers returned back to Chisinau in 1945, after Chisinau was liberated from Germans. That is what you can see here is the air photography of that same part of Chisinau made by Germans in 1944. And you can see that actually that old part of the city was completely destroyed. It was ruined. That is the place where Bersukers originally lived, but that building was destroyed. So they actually settled up in a small house nearby, even closer to the river shore. And Bersuker's father actually repaired the house where they lived, prepared for the winter time, and that was the only mean to live at that time. At that time, in 1945, the 17-year-old young man with just the primary school education, barely able to speak Russian, Isaac enrolled in the Commercial Technical College, and in 1946, in the 10th grade of a night school. After 2 years of self-educated study, Isaac passes the 4 maturity exams, math, physics, Russian literature, and English, which opened the doors to enroll in Chisinau State University. Well, to the left, you can see the first building of Chisinau State University. Originally, it was Chisinau Technical School. The photo is of 1899. And probably the most prominent person in his university studies was Professor Perlin. You can see him in the middle photograph. He was a young theorist, arrived from Kiev to Chisinau, started theoretical physics, and soon he became the chair of theoretical physics department. To the right, you can see the first graduates of the Department of Physics. And here, the red arrow shows the young Isaac. The blue arrow probably you'll recognize is Viktor Kovarsky. After the 4 years of education in between before the 5th year of his education, Bersuker went to Kiev for 1 month to work as a pre-diploma, master's thesis work in the lab of Pecker. You can see his picture in the left side. That is Professor Solomon Pecker, a full member of Ukrainian Academy of Sciences, friend and co-author of Lev Landau. At that time, Pecker was involved in building some kind of theory of semiconductors, and his idea was separating slow conduction electrons from other core electrons of the crystal. And that idea happened to be important to Isaac because he believed that it can be applied to atoms and molecules, not just to crystals. In 1951, Isaac married Lila, a chemistry student, and after graduation, 1 year ahead of Isaac, she was assigned to work as a chemist technologist in Voronezh, a Midwest Russian city of about 400,000 people. As a benefit for married couples, Isaac was allowed to seek a job in the same city, so he moved to Voronezh. He found a job. It was a 1-year job as a physics teacher in a local school of aviation in Voronezh. Soon Lila got her parental leave and returned to Chisinau, and Isaac followed her and applied for a teaching position in Moldova. His second job was a physics instructor in a 2-year college in Soroka, a small town of about 15,000 people at the north of Moldova. And then his third job in 1954, 1955, probably up to 1956, was a physics faculty in pedagogical college in the small city of Belz, with population of about 600,000 people. One important thing has to keep in mind. At that time, Isaac kept working on his idea of applying adiabatic approximation to separate slow-moving valence electrons from the core electrons. So in summer of 1955, if I'm right, he decided to go to Moscow to read some literature, some scientific literature, because in Belz, no scientific journals were available to read. So he went to Moscow, and reading the journals, he realized that most important people in that branch of science were in St. Petersburg, in the Leningrad State University. So he decided to just go there and find someone from Leningrad State University to talk about it. That was his first move, and his next move was to St. Petersburg. The head of the Department of Quantum Chemistry, Quantum Mechanics in Leningrad State University at that time was academician Fock, Vladimir Fock, well-known, famous theorist, famous for his Hartree-Fock approximation. So he approached Fock and his associate, Professor Veselov, with his ideas of adiabatic separation of electrons, of valence electrons from the core. And they were so impressed with his ideas that he was invited for 1 year postgraduate schooling in Leningrad State University. So he applied, he was there for 1 year, and that 1 year, during that 1 year time, he was engaged in atomic spectroscopy and was able to create work which is still cited by people in international journals, even today, 65 years from that time. That was the idea of the polarization of core electrons by the valence electron moving on the far orbit of the same atom. So that was the case when an example was when asking the right question and finding the correct answer remaining persistent and going and impressing people allowed Isaac to achieve an impressive result. He was able to defend his PhD thesis in 1 year of work, after 1 year of work, to create and defend his PhD. And let me tell you, to my understanding, the scientific council that was accepting his PhD and granting him the degree was very tough, probably the toughest at that time in Soviet Union. Then Isaac went to Belz, where he worked for another year or two. And as he described in his speech before me, that was the time when Moldovan Academy of Science was created. And within that Academy of Sciences was decided to create the Institute of Chemistry. Here is the picture of Jahn Grosul, who was the first president of the Academy of Sciences in Moldova. And at the bottom, you can see Professor Ablov talking to Jahn Grosul. I guess that probably they were discussing the issue of inviting Isaac Bersuker to Institute of Chemistry, newly created Institute of Chemistry of Moldova. To the right, you can see the first fellows of the newly created Institute of Chemistry. The blue arrow shows Professor Ablov. The red arrow shows Isaac Bersuker, and the rest of these people, those who worked in the Institute of Chemistry, probably will be able to identify. Well, Anton Ablov was a very important figure in inorganic chemistry with lots of ideas, and working with him was really important for Isaac's future, because at that time he was able to apply his knowledge and experience in adiabatic approximation to coordination compounds. And soon he came to the idea of spontaneous symmetry breaking in transition metal sites with degenerate ground states, known today as the Jahn-Teller effect. During this period of time, he submitted and published more than 24 papers in scientific journals of all union value. And also, together with Anton Ablov, they wrote that book shown to the right. Still, I consider, after all the years, since 1962, there are no wrong statements in that book. It does apply to our today understanding of the properties of coordination compounds. Then, in 1964, Isaac created the lab of quantum chemistry, an important part of the Institute of Chemistry. To the left, you can see the building of the Institute of Chemistry of Moldova, built up by that time. And I remember the lab where Isaac's, on the floor, fourth floor theorists were assigned rooms on the fourth floor, because it was believed that theorists don't need any kind of equipment to bring up to the upper floors. So in the right side, you can see the building where Isaac lived for a long time on the central street of Chisinau. It's exactly across the monument of Stefan cel Mare, Shisfund. And interesting enough, that building has a historic importance, because originally it was the famous, before 1940, it has been the famous Hotel Swiss. So during that time, in 1964, he earned his doctorate degree, second doctorate degree. In Russian, it's called Doctor of Science degree. In 1972, he was elected as a corresponding member of the Academy. In 1989, he was elected as a full member. During this period of time, he published more than 250 papers and 6 monographs in the field of quantum chemistry. And he directed about 30 postgraduate students who defended their PhD thesis under his guidance. In the left side, you can see the first fellows of the quantum chemistry lab. In the right side, you can see more people, more fellows of that lab in a later time. Well, he mentioned already that in 1978, the license of discovery of tunneling motion due to the Jahn-Teller effect was issued to the Institute of Chemistry. Hello? Is it all right? I hope it is. And due to the world-recognized leadership of Bersuker's lab in the field of vibronic interaction, it earned the unofficial title of the Kishinev School of the Jahn-Teller effect. And Kishinev at that time was called by some the capital of the Jahn-Teller effect. The 10th International Symposium on the Jahn-Teller effect held in Chisinau in 1989 with Bersuker as the chair of its organizing committee. And from this time on, as a world recognition of Bersuker's leadership, Isaac has become the permanent chairman of the International Steering Committee of the Jahn-Teller Symposia. During his American period, when he moved to the United States in 1993, let me move back. Well, it's okay. Let's go. Well, I'm coming to conclusion, and by all means, Isaac is a self-made man, and the secrets of his productivity and great accomplishments are family values and family support, perseverance and persistence, hard work, 95% of sweat and 5% of good luck, creative ingenuity, curiosity and inquisitive attitude. And as Richard Feynman said, scientific knowledge is a body of statements of varying degrees of certainty, some most unsure, some nearly sure, none absolutely certain. And that all his life, Isaac was in the pursuit of the scientific truth. And at every time it appeared that he got it, it disappears, demonstrating unexpected complexity of the nature. Well, acknowledgements. I want to thank Isaac Bersuker for the information he provided me, Eugene Kowarsky for some interesting photographs, and also some maps and photographs were borrowed from the website alt.chisinau.com. Okay, thank you for your attention.
Thank you. Thank you, Professor Victor Pollinger. It's very interesting CV, very good, very impressive biography. I think this biography can be a story of our country. Story of our country is very interesting. Thank you so much. And I propose to publish these materials and maybe in Moldavian or academician journal Academos, or in our Moldavian journal Chemistry of Moldova. It's very interesting biography. Any questions, please? In our small room or other? Nothing? Okay, thank you so much again.
Thank you.
Thank you so much. Very good biography. Congratulate you and the academician Bersuker. I invite to the floor Gorenchoi Natalia, Institute of Chemistry, pseudo-Jahn-Teller effect and transition states of redox processes. Please, Natalia.
Dear Chairman, thank you for giving me the opportunity to speak at this meeting. At the beginning, I would like to say a few words to Academician Bersuker. Dear Isaac Borisovich, it is a great pleasure and honor for me to work with you for several decades. For me and for all of us, your disciples and followers, working together with you is great luck for us and means the highest class research of various aspects of the Jahn-Teller effect. You are not only the founder of our world-famous laboratory of quantum chemistry, but also the generator of scientific ideas which over the years are inspiring generations of researchers around the world. My presentation today is connected with the study of the redox processes relevant to environmental problems. First of all, I would like to mention that the idea of the pseudo-Jahn-Teller origin of the instability of the transition state of chemical reactions and the existence in this configuration of stable excited states that cause the instability of the activated complex was put forward by Academician Bersuker back in the 18th in the last century. For a simple exchange reaction between an atom and a molecule of hydrogen in linear collision, this conclusion was confirmed by us by the direct electronic structure calculations of the transition state and numerical calculations of the vibronic constants in the nuclear configuration at the maximum of the barrier. Опа. Так, pardon, что я снова? Да. Ага. Что такое там красное? Да, это самая какая-то там строчка. Ну, ладно. Most of the process in the environment involve either electron or proton transfer or both. In some more recent work, the pseudo-Jahn-Teller effect was shown to control the proton transfer between two molecular systems, often termed as a hydrogen bond. This approach in turn allowed us to estimate the main parameters of the hydrogen bond, the energy barrier for the proton transfer between the interacting molecular systems. The first system we considered is a bifluoride anion. Earlier, it was established both experimentally and by quantum chemical calculations that this anion is linear and centrosymmetric in the gas phase, whereas in the crystal structures, the shifts of the proton from the midpoint are often observed. The investigation of the anion was started from the reference configuration of the D-infinity H symmetry. The geometry optimization has confirmed that its equilibrium nuclear configuration with the equilibrium fluorine-fluorine distance equal with 2.24 angstrom corresponds to the symmetrical position of the H atom exactly in the middle of the fluorine-fluorine distance. At the same time, with increasing distances between fluorine atoms, this D-infinity H configuration of the anion becomes unstable with respect to symmetrized sigma U displacements of its atoms. From table 1, it can be seen that with the increase in the distance, the height and width of the barrier to proton transfer are also increased. At the fluorine-fluorine distance of about 3 angstroms, the barrier to proton transfer becomes sufficiently large, and the proton is localized in an off-center position, as for example, in the two demonstrated complexes of aluminium and palladium. Oh. Так, да, да. Yes. The ground electronic state wave function of the system belongs to the sigma G representation of the D infinity H symmetry point group. According to the Jahn-Teller effect, the excited state that produce the instability of the ground state should have the symmetry sigma U. In order to reveal the Jahn-Teller origin of the proton transfer in these systems, we have calculated the energy profiles along the coordinate of instability for the ground state and the excited states of sigma U symmetry. The results for several fluorine distances are shown in figure 4. One can see that really at equilibrium, the adiabatic potential is a single one, meaning that the proton is located in the middle between the fluorine atoms. Two other curves in figure 4 are the cuts of the adiabatic potential surfaces for the fluorine distance is equal to 2.64 angstrom and 2.84 angstrom respectively. It is seen that the energy profile of the corresponding sigma U excited state admixed to the ground state in the Jahn-Teller effect have a minimum in the nuclear configuration of the transition states. The parameters of the Jahn-Teller effect were estimated by fitting the general formula 1 obtained from the Weber-Brownick theory to the ab initio calculated energy profile along the sigma U coordinate. Sure. The next task was to demonstrate the Jahn-Teller origin of the proton transfer energy barrier in the deprotonated and protonated water molecules. For the dihydronium cation H5O2+, the starting symmetry configuration is the D2D1. In this geometry, the out of center displacement of the central proton towards one of the oxygen atoms is a B2 type distortion. The ground state wave function of the dihydrogen cation belongs to the A1 representation of the D2D symmetry point group. Then only excited state of B2 symmetry contribute to the instability of the D2D configuration with respect to this distortion. Calculations of the total energy of the system as a function of the proton displacement are shown in figure 7. It is seen that at the equilibrium distance or oxygen-oxygen, this potential energy is a single form. This means that the shared proton is localized, it's midway between the oxygen atoms. But with increasing the OO distance, the potential energies become the double well ones. Again, the calculated parameters was The parameters of the Jahn-Teller effect was calculated by fitting calculated values to the general formula. In the cluster in which the dihydronium cation is surrounded by 4 water molecules, the equilibrium oxygen-oxygen distance is equal to 2.38 angstrom, and calculations show the presence of one imaginary frequency which corresponds to the off-center proton displacement, leading to the stable C2V nuclear configuration of the clusters. Thus, taking into account only the first acceleration sphere around the Zundel cation, leads to a double adiabatic potential energy surface along the hydrogen bond coordinate and to the instability of the central position of the proton. To reveal the pseudo-Jahn-Teller proton transfer in the H3O2 we started with the high symmetry planar nuclear configuration of C2H symmetry. Our initial calculations of the system in this configuration have shown that it is unstable with respect to 2 nuclear displacements. The distortion of the BU symmetry corresponds to proton motion along the OHO hydrogen bond and leads to the planar nuclear configuration of CS symmetry, figure 10. The second distortion of AU symmetry corresponds to the outer plane displacements of the atoms, resulting in the symmetrical C2 structure. In their turn, both CS and C2 nuclear configurations are also unstable. The first one of CS symmetry is unstable with respect to the A double prime distortion, leading to the equilibrium C1 structure. The nuclear configuration of C2 symmetry is unstable with respect to displacement of the central proton towards one of the oxygen atoms, and also resulting in the equilibrium C1 configuration. Every step in the sequential symmetry breaking in figure 14 is accompanied by a decrease in the energy of the systems shown in figure 15. It is seen that the proton transfer in the hydrogen bond in this system can take place in both planar C2H nuclear configuration along the BU coordinate and in the configuration of C2 symmetry. For these two distortions, the corresponding cross-section of the adiabatic potential surfaces for the ground and corresponding excited states were calculated. In both cases, it was shown that the instability of the central position of the proton is owing to the pseudo-Jahn-Teller effect. Moreover, calculations also show that for each fixed torsion angle between the two HO planes, the intermediate nuclear configuration of C2 symmetry are also unstable with respect to center protons transfer. In figure 14, the potential on the surface of the ground state of the considered an ion in the two-dimensional space of the two normal coordinates of twistings and displacements of the central proton towards one of the oxygen atom is shown. The role of the Jahn-Teller effect and the pseudo-Jahn-Teller effect in the electron transfer triggered processes can be demonstrated on the example of the formation of coordination compounds, which is accompanied by the electronic density redistribution in the activated complexes. One of such examples is the formation of an intermediate complex of rhodium in the reaction with the white phosphorus. Calculations have shown that the geometrical structure of coordinated P4 molecules is significantly changed by its coordination to the complex. One of the P bond is broken and the tetrahedron P4 is open to form the butterfly geometry. From the correlation diagram between the molecular orbitals of the complex and those of its fragments, it is shows that in the transition state, electron density is transferred from the d orbital of rhodium atom to one of the unoccupied triple degenerate T1 orbitals of white phosphorus molecule. This leads to a non-zero distorting force acting on the phosphorus nuclei in the new electron distribution. This force triggers the T2 type distortion, resulting in the observed butterfly geometry of coordinated P4 molecules. This distortion is accompanied by a decrease in energy, thereby stabilizing the intermediate complex. The role of the Jahn-Teller effect in the transition state of chemical reactions can be demonstrated by the example of formation of the iron complex with the formaldehyde, in which the H2 coordinated molecule is distorted to a non-planar pyramidal shape. Again, from the correlation diagram between the molecular orbitals of the complex and those of its fragments, one can see that as a result of coordination, the lower unoccupied 2b1 molecular orbital of formaldehyde molecule acquires the charge 0.52 electrons. Since the distortion mode leading to the non-planar configuration of formaldehyde molecule is also of the B1 symmetry, the orbital Wabronic coupling constant mixing the partly occupied 2b1 orbital with the unoccupied 6a1 orbital becomes non-zero. Then the curvature of the adiabatic potential of coordinated formaldehyde molecule with respect to bending mode can be estimated approximately by equation 2. With calculated values of all the necessary parameters of this equation, we get the negative resulting value for the curvature of the adiabatic potential of coordinated molecule with respect to the bending mode. It means that the formaldehyde molecules is distorted to a pyramidal structure with an energy gain, thereby stabilizing the complex. Thus, it was shown that the properties of the main attribute of chemical transformation, the transition states of chemical reactions, are controlled by the vibronic coupling between its ground electronic state with the appropriate low-lying excited state, leading to the Jahn-Teller effect.
Thank you.
In conclusion, on behalf of our theoretical group of the Laboratory of Physical and Quantum Chemistry, I would like to express to academician Isaac Bersuker our deep gratitude and appreciation for cooperation and support, congratulate him on his wonderful 95th birthday, and wish him for the creative success. Thank you for attention.
Thank you, Natalia Gorjay. Great presentation. This is the results of the thesis of Dr. Habilitatus, and Natalia she is ready to present more, to present the thesis in public discussion. And Natalia Gorinchoi present a very interesting direction in our Laboratory of Physical and Quantum Chemistry. Electron and proton transfer and redox processes, and she tried to combine Marcus and Jahn-Teller theory, and Isaac Bersuker helped Natalia very good. Thank you, Isaac Borisovich, and congratulate for Natalia. and I wish success to sustain the thesis of Dr. Habilitatus. Thank you so much. Any questions, please? No? Thank you. I want
one
to
moment,
say,
please.
please.
Greetings
Online, please.
from Bucharest.
Oh, yes,
And,
okay.
again,
Dr. Fenik Cimpoiescu.
let me just point something. The hydrogen difluoride can be considered the smallest coordination compound because you know a coordination compound is with something positive in the middle and some negative or polarized ligand aside. So hydrogen difluoride and dihydronium can be considered coordination compounds. And please let me express my desire for a joint cooperation with Natalia, Professor Gorinchoi, with Professor Bersuker and Professor Duca, if possible, because we are also interested in re-expressing Marcus theory in terms of vibronic coupling. So I hope maybe in this year or next year, maybe you can discuss and concretize something about.
Thank you. Thank you. Natalia, some comments? No? No? Thank you. Thank you for this compliment. Okay. Not online. Other questions? Not. The next, I would like to give the floor to Liviu Cibotaru, dynamic vibronic order on the emergent magnetism cubic double pervoxetous. Please, Professor Cibotaru.
I will.
Before you you begin to speak, I want to say, if somebody, not organize coffee break or tea break. If somebody have to coffee or tea online at home, at office. Here, small room. Vice President Svetlana Kojukaru says, have the tea and coffee here, and the last of our big table. Thank you so much. Please, I give the floor to again to Liviu Cibotaru, Professor Liviu Cibotaru.
Thank you. I hope you can hear me. From the beginning, I want to thank the organizer for inviting me to this nice workshop, celebrating the 95th birthday of Professor Bersuker. I was a PhD student of Professor Bersuker, and then I worked another 10 years in his lab. So I was formed during this time as a researcher, and I felt the support and the advice of Professor Bersuker for many years, and actually till now. So I think this can be said by any member of our Laboratory of Quantum Chemistry in Chisinau. I would like to present today some results on our study on dynamic vibronic order in Jahn-Teller crystals. So this kind of order is formed in dynamic cooperative Jahn-Teller systems. So we are considering crystals with Jahn-Teller unit cells of Jahn-Teller centers in each unit cell. Before, let's remind shortly what is a static or cooperative Jahn-Teller effect, or a classical cooperative Jahn-Teller effect. So, for some temperature, lower than some critical temperature, Such crystals with Jahn-Teller centers, they undergo structural phase transition, during which the symmetry of each unit cell is lowered, and the crystal entirely acquire lower symmetry. And then here is shown in the figure what happens with the adiabatic potential of each Jahn-Teller center of molecule in such crystal. So the lowering symmetry of the crystal impose some molecular field, which arise mostly via the elastic interaction between the molecule and crystal. And what we see is that, for instance, for pseudo-Jahn-Teller centers, one of the wells will be lowered by a value energetically equal to molecular field. Then one of the levels which form the tunneling states in such a pseudo-Jahn-Teller system gets lowered, and in some moment it becomes localized in this well. So in this moment we have a wave function which is the vibronic wave function becomes a simple Born-Oppenheimer wave function. So we have just a product of adiabatic wave function. This is electronic wave function corresponding to the given point minimum where it sits in the localized state, and multiplied by some harmonic vibrational function, small oscillation around this point. Because we have, in this case, we have a one-to-one correspondence between static distortion, which correspond to the point 2,0 of this molecule, and the orbital ordering, which is just the adiabatic electronic function in this point 2,0. The crucial point for this picture is that the localized level is lower than the typical energy separation between vibronic levels in isolated molecule. So this is here is a tunneling splitting. If this separation is not sufficient, what you will see the delocalization of a system on the second wall. So you will have only partly localized, or in other words, unquenched dynamic Jahn-Teller effect. This effect is stronger in systems which are not of multi-wall type. For instance, the linear E problem, if we apply some molecular field, we'll see that here it's exaggerated, of course. We see that the minimum, the continuum of minimum, the ground, say in the bottom, will get a bit inclined. So some region will be lower in energy, but this region is quite flat. So to obtain a good localization, you need to mix not only two tunneling states, but a bunch of states, of Jahn-Teller states, which is in the energy interval of about, say, close to Jahn-Teller energy. So actually, the most cases for such a system, when we have no common atom, the molecular field is sufficiently weak to localize even one state. And then we have a situation that even the ground vibronic state, it is still delocalized in such a way that it occupies all the trough region. So in this case, we have a situation that we have ordering, but the ordering will be of some combination of vibronic states levels in the ground state. So it will not be an ordering of static distortions, but it will be a kind of ordering of vibronic states on sides. So this means that it will be stabilized one certain combination of vibronic states in the ground state of each molecule. So this is called dynamical vibronic order. Its signs are weak static distortion, because during such a delocalization, even in distorted potential. The average value of any static distortion is close to zero. We'll hardly observe them even in X-ray analysis. And of course, we have a suppressed orbital order because now the system in the ground state, it is delocalized in different points of the trough. So we actually see the superposition of all possible combination of electronic functions. So we have no orbital order. A typical, so one situation of this type are cubic fullerenes. These are A3C6 alkyl doped fullerenes. So we have 3 electrons from an alkaline atom going to C60 molecule and occupying 3 orbitals of T1U symmetry. This is a LUMO orbital. This is at each site. We have a Jahn-Teller effect of T1U HG type. HG is a 5-fold degenerate vibration in icosahedral symmetry. This is symmetry of a C60 molecule. Then due to this Jahn-Teller effect, we have a splitting of orbitals in three adiabatic orbitals. And the splitting is larger than Hund rule. So in a pure electronic system, Hund rule stabilized spin 3 half. Due to splitting, Jahn-Teller splitting, the of-bow population of the levels will give us spin 1 half. And due to strong Jahn-Teller effect in this molecule, the wave function is of strong coupling form. So it is corresponding to rotation in the trough. The trough is 3-dimensional. So it is after the coordinate gamma, theta, and phi, angular coordinate, but in the ground state, it is delocalized only after theta and phi. And we have a 3-fold degenerate vibronic level, like can be characterized by angular vibronic moment, taking the value -101. So if we consider systems like expanded fullerenes, this are cesium-3 C6 or this ammonia expanded fullerene, the distance between fullerene in the crystal is sufficiently large that we have the Mott-Hubbard localization of electrons. So these are not a band structure anymore, but localized electrons on sites. And we know very well in this case the physics of the lowest excitation is described by exchange interaction. So the exchange interaction between 2 sites with non-degenerate orbital non-degenerate sites is the Heisenberg exchange Hamiltonian, which is very well known in our lab because many magnetic molecules have been investigated in the Institute of Chemistry. So this is described by this term in the brackets, a pure spin term. But besides, we have now 3-fold or vibronic degeneracy of sites. And because of this, the operator describing the exchange between 2 sites should include different situations. And the system on one side and another side can sit in one of its 3 states. So we have a total 9 combination. So instead of a constant here, we have an operator, a matrix of the dimension 9 by 9, describing the spin vibronic super exchange. If we analyze these operators, then what we see is that they can be expressed via the quadrupole vibronic operators. So, and the expression looks like exchange, like interaction between different quadrupole vibronic moments on different sides, much like say, exchange interaction between spins, but this is of very anisotropic type. So what are these quadrupole operators? Quadrupole operator, this is a familiar formula for the quadrupole operator, momentum operator expressed via angular momentum operator. These are vibronic angular momentum. And we have 3 such operators which are involved in this super exchange interaction. They correspond to Z, X, and Y. So together they form a kind of vector. So because of interaction between this quadrupole, we have the say, ordering of them. If the temperature is low, sufficiently low, we have an ordering. And this is like we have an ordering of spin in ferromagnetic or antiferromagnetic magnetic materials. Here we have the ordering of these quadrupole moments along, say, on each side, along some direction. So depending on the parameters of relation between the transfer parameters, between electron transfer parameters, between fullerenes, we can have two situations. We can have a ferromagnetic ordering of quadrupole moments with direction along the diagonal of the cube, and we have antiferro ordering with direction along, say, the cubic axis. The calculations have shown that for lithium expanded fullerite, the situation is the ferro ordering of these moments. And exactly like in ordered ferromagnetic or antiferromagnetic materials, we can have excitation, some waves, but this will be already waves of vibronic magnons. So instead of magnons, in the normal magnetic materials, we have excitations of this from this order. So these are dispersion of such excitations. So they are called optical magnons of vibronic origin. So these are two branches of such. So it looks like exactly like a situation in magnetic materials. The main effect which we can say extract from this interaction is the vibronic reduction of exchange interaction, because the sites are in vibronic, say, vibronic states. You know very well there is an effect of vibronic reduction for all physical quantities. Here we have the vibronic reduction of exchange interaction. As a result, we have an what is reduced much is reduced the orbital anisotropy of exchange interaction, and we obtain an almost isotropic, simple isotropic antiferromagnetic exchange. And this is confirmed in experiments. So have been done measurements. They found antiferromagnets, and in paramagnetic phase, they proved that this is an isotropic. So this is the direct consequence of dynamical Jahn-Teller effect on sites. Otherwise, if you don't have Jahn-Teller effect, we have the so-called spin orbital exchange interaction, a kind of Kugel-Homsky model. And if we try to, with the same parameter, calculate what kind of spectrum we will obtain, it is very much different from what we see actually in C63 minus. So the vibronic, the effect of dynamical Jahn-Teller effect influence very much the levels in the spectrum in these systems. Another system which I want shortly to mention is the D1 double perovskites. So these are perovskites, octahedral without common atoms. Therefore, they are prone to display dynamical Jahn-Teller effect and dynamical order. So we have one electron in T1G orbital, T2G orbital, sorry. This, due to very strong spin orbit coupling, we are here having in the center of octahedra rhenium, tantalum, and many other heavy. So this is a big family of compounds, actually. So we have strong spin orbit coupling and stabilization of gamma 8 term multiplet. And we know for gamma 8, there is a Jahn-Teller effect gamma 8 with E distortions, like shown here. There are also T2G distortion, but E are dominant distortions. Usually, this is pure gamma 8, gives you a trough in like EE problem. It's just a trough of the minima and the lowest adiabatic potential energy surface. But here we have also pseudo Jahn-Teller effect, gamma 8, gamma 7. Then we have also some effects due to T2G vibrations. So altogether, if you project everything on gamma 8, you obtain that this will be a bit, will have some minima, will be a bit warped, the surface. So in this case, the lowest vibronic states here these are vibronic doublet, and we have a singlet, which is at some distance. So these are the lowest vibronic level. It corresponds, basically to hindered rotation of deformation in such system. How to describe orbital, say, vibronic and magnetic order? So we use the representation of gamma 8, which is known. It is a direct product of gamma 3 and gamma 6 representations. Gamma 6 is a pure magnetic. It is the irreducible representation of Kramer's doublet in a cubic symmetry. Gamma 3 is our known E doublet, orbital doublet, but here it's pseudo-orbital. Doublet is not pure doublet, and this is not a pure spin. This is a pure, the symmetry structure can be represented like this. And then all Jahn-Teller effect will be only with this tau, two-dimensional representation gamma 3. And it will go via Z and X. These are sigma Z, sigma X matrices in E problem. And also this tau will describe the quadrupole moment operators, which if we, in the space of free chosen lowest vibronic state, they will give us the quadrupole operator, which will describe the vibronic order in these systems. So average value of this operator will describe the quadrupole order, vibronic quadrupole order. Well, here is the result of the calculation without details. This is how looks the diagram. This is the last slide. So this is how looks the phase diagram of such a system as function of two basic parameters, d and theta. So these are parameters describing the elastic coupling between the Jahn-Teller distortions on sides. In experiment, there are all this family of perovskites, they display either of the two phases. This is FM110, it is shown here, how it looks, and AFM FQ, so antiferromagnetic in the spin sector and ferro quadrupole in the vibronic sector. So it is shown here. So depending on these parameters, different systems can stay either here or here. One of them will be, this is completely in line what is observed in experiment. So if you don't take into account this elastic coupling, the elastic coupling you have to take into account if you consider the vibronic model. So in this case, we will never obtain this phase, which is at odds with the experiment. So for temperature different from zero, how behave the temperature behavior of these order parameters. So they are shown here. These are vibronic, quadrupole order parameters, there too. And there is a magnetic order parameter. This is for ferromagnetic phase of the sublattices. We have the thumb. We see that with temperature disappear first the magnetic ordering. And then at much higher temperature disappears the ordering of vibronic quadrupoles. The same for another AFM phase. Yeah, you can see it's very similar. And in experiment, they indeed can measure the two-phase transition by just making calorimetry. In calorimetry, we can measure the specific heat. Specific heat has a jump at the point of transition, second order phase transition. And you can judge the existence of two order parameters in this system, which is nice. So in principle, the vibronic theory can explain the entire the behavior of these two order parameters in this series. Okay, so this was a short overview of what we have done. This is a summary. So the dynamic vibronic order actually is a new type of order. It is not as new as it's not recognized, because the general feature of Jahn-Teller effect long time was that it was not observed. So many people didn't believe in Jahn-Teller effect, and especially in dynamical Jahn-Teller effect. Something like this happens now with magnetic materials. So There is a way to observe them directly. An experiment, this is high resolution resonant X-ray scattering. So you can probe directly these phases. But there are signs to observe this dynamical vibronic order. First of all, by small or even non-existent Jahn-Teller distortions. So if you know for sure that there should be Jahn-Teller effect, and you don't observe anything in X-ray or in other experiments which probe the distortion, for sure you have a dynamic Jahn-Teller situations on site. And second, which is also very interesting, the orbital anisotropy is strongly reduced. So in such a systems, you always will see isotropic magnetic interaction. There will not be some phenomena like orbital anisotropic interaction, like in spin orbital exchange, like in Kugel-Homsky model. What are the conditions? First of all, we have to have essential non-adiabaticity on site. So it should not be a kind of EB problem or TE problem, where it's, say, non-adiabatic system. Second, the most probable candidates, these are crystals without common atoms. And actually, there are already many observed, already studied, like cubic Fullerized and D1 double perovskites. There are also other systems where we expect that there is a dynamic Jahn-Teller effect on sites in the ground state. So these are hexagonal layered perovskites, and there are many other. I would like to end my this presentation by moving actually to a topic which is more appropriate to our webinar. We know very well that Professor Bersuker made groundbreaking contributions to Jahn-Teller science. And besides, he wrote many books, as was mentioned today, on Jahn-Teller effect, comprehensive books for different communities, for chemists, biochemists, material scientists. And this is one of the first books on Jahn-Teller effect. It was written for physicists. And I have to say that this is nowadays is one of the most popular books in molecular physics. And for sure, this is a reference textbook for any theoreticians working in the domain of Jahn-Teller effect. So on behalf of all of them, I would like to thank Isaac Bersuker and Victor for this brilliant piece of science. Thank you for your attention.
Thank you for great presentation. Very interesting presentation. This is a high results, high presentation. Any questions? Please, Professor Ursaki.
Could you please let us know if some kind of very interesting ordering effects have been proved by X-ray scattering?
Well, X-ray scattering just proves that it doesn't exist. If you see the distortion X-ray scattering, then most probably this is a static Jahn-Teller effect. Of course, there are intermediate situations. Directly in X-ray, you can prove this, for instance, if you have dynamical Jahn-Teller effect in, say, pseudo-Jahn-Teller, in a crystal with pseudo-Jahn-Teller sites, and you have dynamical Jahn-Teller effect on this pseudo-Jahn-Teller. Well, at high temperature, this is for sure that it will be like this. Usually in X-ray, they just, when they construct this pattern for scattering, they suppose the position of atoms, two positions of atoms, corresponding to distortions on one well and another well. So in this way, they obtain much better R factor, the reproduction of the scattering pattern. I have seen such work; they are known, but this is quite difficult thing to do. So there are the direct ways to probe dynamical Jahn-Teller effect by say doing X-ray, especially dynamical order. It's doing X-ray scattering, resonance X-ray, both elastic and non-elastic. You can get a lot of information. Yeah.
Other questions? Livio, can I ask you, Was Liviu Ungur your PhD student?
Yeah, he was my student and PhD student. He's now professor in Singapore University.
Singapore. Very good, very interesting. Another question. Do you know you are a member of board of Journal Chemistry of Moldova?
Yeah.
Journal Chemistry of Moldova. Board member.
Yes.
Do you know?
Yes, yes, I know.
Can I ask you next 4-6 months to send for the Journal Chemistry of Moldova one article like this presentation?
Okay,
Or this
okay.
presentation like
Yeah,
article?
this is planned. It was announced that the presentations will be published in some special issue. So I'll present with pleasure this material.
Okay, Liviu Cibotaru, Professor Liviu Cibotaru. My opinion, I think you must to be honorable member of Moldovan Academy of Science.
Well,
This is my opinion. because you are Moldavian, you have very good results, very good results. What is your Hirsch factor?
It's 68.
You know?
For Web of
Oh.
Science, it's 68. For
Very good. Thank you so much. Other questions? No, thank you.
Yes.
Another question.
Yes. May I have some question?
Please, please.
Yes, thank you very much for a very interesting talk. I think we have some experience in studying the ground states of vibronic systems, magnetic vibronic systems, such as lanthanum manganese oxygen-3, YTO3, and others. And I think it's not a simple question to say if you have your ground state in vibronic coupling, or it is due to exchange interaction. So, and actually, there is a hint, since you have this symmetry breaking phase transition at much higher temperature, usually, than magnetic ordering temperature. So this means that the Jahn-Teller interaction is stronger than super exchange interaction. And so then it is the main driving force for the orbital ordering itself. And magnetic ordering, which happens at much lower temperatures, just simply some small addition to the fine orbital tuning, which occurs and paves the way to magnetic ordering. But the state, this ground state, which is coupled both to vibrations, lattice vibrations, and coupled to magnetic interaction at lower temperatures, it's very interesting state, actually, where we have this very different physics and interactions, and they are all involved. Concerning the D1 system, you mean it should be triply degenerate state or not in these compounds you have considered? D1 system,
yes,
is triply degenerate state initially,
it's
or
triply degenerate. Yes, it's a cubic system, and each these are cubic symmetry. Each octahedra is in cubic environment.
Then you have to probably consider different types of Jahn-Teller problem, or coupling to E modes, or coupling to T modes. when you have D3D type distortions along your cubic diagonal.
Yeah.
Or you have just classical, this Jahn-Teller modes, Q epsilon or Q theta, like in Mexican hat.
Yeah.
So, and the system can be either in this state, either in other state. So have you considered also these different ground states due to these different situations?
Thank you, Natalia.
Yes.
If you are interested, we can get in touch by email and discuss all this, because now there is no time.
Yeah, it's very interesting to discuss with you this problem indeed.
Yeah. Okay.
Thank you. And also, I would like to congratulate Isaac, Professor Isaac Bersuker, with his 95th birthday. And I am actually excited always to have discussions with him and his absolutely unusual approach in science. So it's like intuition, or I think it's something else from God. So wish you further success in your creative work, and we hope you will invest many more ideas for scientific future of human being. Thank you.
Thank you, Natalia. Thank you.
Thank you very much.
See you, Hunter. Okay, thank you. And some comments, Levi, or is enough?
Well, I propose to get in touch by email, because Natalia has many questions and we can discuss.
Good.
Or by Skype. Yeah.
We can go ahead. Next word I give to Young View. Young View online? Yes? Okay, please. Pseudo-Jahn-Teller effect in photochemistry and catalytic activity. Very interesting.
Can you hear me?
Yes.
Good morning, good afternoon, good evening, dear professors and friends. I'm Yang Liu from Harbin Institute of Technology, China. The topic of my presentation is pseudo-Jahn-Teller effect in photochemistry and catalytic activity. Before my presentation, I would like to introduce myself first. I work with Professor Bersuker as a postdoctor in University of Austin, United States, from 2008 to 2010. It was my first time to know about the pseudo-Jahn-Teller effect, and the 2 years training supervised by Professor Bersuker is also a good memory for me. Since I was back to China in 2012, I still work with Professor Bersuker on this project. Today, I'm so honored to join the webinar to celebrate the 95th birthday of Professor Bersuker. My research is mainly focused on the theoretical and the computational chemistry. My first theoretical paper to recognize the important role of pseudo-Jahn-Teller effect in linear molecule was published in 2010. This finding broke the traditional understanding for the Jahn-Teller effect. Continue my interest for linear molecule, we found a novel phenomenon induced by PJTE for some special linear molecule with delta ground state in 2014. It was called broken cylindrical symmetry. And in recent years, we explored the applications of PJTE in many chemistry fields. Today, I'm going to share my studies related to the PJTE with 3 typical applications in photochemistry, energy chemistry, and materials chemistry. In chemistry, in chemistry and the biology fields, there's a general question: why and how does light induce reactivity? The system becomes chemically reactive by excitation due to its polarization. The process is called sudden polarization. We found the sudden polarization is induced by the pseudo-Jahn-Teller effect in the excited state interacting with higher excited state. The pseudo-Jahn-Teller effect is triggered by many nuclear vibronic mode for many organic molecules. For solving the multi-mode problem, we propose the concept of interactive mode, which is the linear combination of coupled modes based on their contribution to the ab initio calculated dipole moment curves. And with this interactive distortion, we can obtain the ground state and excited state energy profiles. And we can also observe the dipole moment of about 0.7 AU on the minimal of the S1 state. In this way, with the similar method, we investigate many organic molecules about the sudden polarization phenomenon, like the ethylene and the butadiene and the stilbene and halogenated stilbene and so on. Then we got a general physical picture for the photochemistry process. Under the light condition, the molecule will be excited to some excited state, and then it will receive the repulsion from the neighbor higher excited state with the nuclear distortion, resulting the structure instability, energy reduction, charge separation, and observe the sudden polarization phenomenon. Finally, produce the chemical reactivity. So in this study, we found that pseudo-Jahn-Teller effect is really a powerful tool to understand and explain and predict the photochemistry phenomenon and the mechanism. Let's move to the application of pseudo-Jahn-Teller effect in energy research. A promising anode electrode materials for sodium-ion battery should have strong absorption and storage ability for sodium, which is significantly affected by the geometry configuration of the material surface. Then the pseudo-Jahn-Teller effect could be a good tool to understand the relationship between the performance and the structure for materials. We found for the two-dimension tin phosphide, the formation of the stable barcode configuration is from the pseudo-Jahn-Teller effect, and the barcode configuration is favorable for sodium adsorption than the planar configuration. And after the sodium adsorption, the material surface received the charge, and at the same time, the pseudo-Jahn-Teller effect is suppressed. So the height of the barcode configuration is reduced, then facilitate the storage for sodium. Therefore, this study explained the origin of the tin phosphide material as a promising anode electrode material for sodium-ion battery by employing the pseudo-Jahn-Teller effect. Finally, I would like to introduce the application of pseudo-Jahn-Teller effect in catalytic chemistry. Taking use of the density functional theory calculations, we designed a biatomic catalyst which shows excellent activity for oxygen reduction with very small overpotential of 0.2 voltage. The promising catalytic activity depends on the good activation for oxygen molecule, which closely related to the asymmetric axial center. Then the pseudo-Jahn-Teller effect could be employed to understand the activity further. The symmetry breaking in the active center of the biatomic catalyst is observed as compared in the figure A and B from D to H to C to V. and it originated from the pseudo-Jahn-Teller effect, which can be seen from the calculated energy profiles in figure C. And the asymmetric configuration could enhance the polarization for the oxygen molecule and further increase its reactivity, which can be seen from the longer oxygen bond and stronger absorption energy for oxygen, as shown in figure D. Additionally, we also found the asymmetric deformation of the active center increases the catalytic activity increases. Therefore, the symmetry deformation degree of the active center could be an important indicator for catalytic activity. Let's make a brief summary. As the biggest progress in Jahn-Teller effect field, the pseudo-Jahn-Teller effect has become a powerful tool for understanding the origins of molecular structure for ground and excited state, predicting novel phenomena, and showing extensive applications for molecules and solid state in many fields, such as physics, chemistry, energy, materials, and so on. It is expected that we could find more and more interesting applications and novel effects related to pseudo-Jahn-Teller effect in future. That's all my presentation. Thanks for your attention. I wish all of you have a happy, healthy, and successful new year. And happy birthday to Professor Bersuker again. Thank you.
Thank you. Thank you so
Thank
much. 10 minutes. 10 minutes. Brave. Any questions? Cool.
Yeah,
Thank you so much.
In China, it's
Yes,
also
please.
it's midnight now. So if anyone has some questions, please contact me by email or within my homepage.
Mm-hmm. And
Thank you.
please online maybe somebody can do. No. Thank you. In Harbin is okay. Is good. Is well. Water.
We are all good. Thank you.
Success. Good luck.
Good luck.
Thank you. I give the floor next speaker, son of my professor, Stepan Stavrov.
That's right.
Very good professor in the dispersed system, physical chemistry of dispersed system. The infrared absorption band of the coordinated carbon monoxide as a probe of structure and dynamics of hem proteins. Please, Professor Stavrov.
I'm sorry, I changed a little bit the title, but anyway, I would like to thank the organizers for inviting me to participate.
We accept, but I like this theme. This term is very good. But accept and use. Please.
Okay. Everybody sees the presentation, I hope. Now, so first of all, I would like to thank the organizers for inviting me, and I would like to stress that I was really lucky to start my scientific career in the lab by Professor Bersuker. It was a great school. I enjoyed it really very much. And everybody talked here about Professor Bersuker as an excellent scientist. That's absolutely correct. However, he was great administrator also. And keeping a lab with about 20 geniuses, it was not a simple task, but he did it perfectly well. Now I would like to start the presentation. And I want to say that all these studies started in Chisinau under supervision of Professor Bersuker. To start with, I would like to start with electronic structure of carbon monoxide. You can see here, this is a sigma band, sigma orbital, which is totally populated in free carbon monoxide, and this is pi molecular orbital, which is empty in free carbon monoxide. This molecular orbital is non-bonding, so its population does not affect the strength of the CO bond. However, the pi molecular orbital is strongly antibonding, and therefore change in the population of this molecular orbital strongly affects the strength of the bond, and this effect can be seen in, for example, vibrational frequency of AB or carbon monoxide vibrational frequency. Now, this picture was understandable for many years, but it's a qualitative picture. Professor Bersuker developed a so-called vibronic activation theory, which allowed to quantitatively analyze how change in the population of these two orbitals affect the frequency and interatomic distances of different diatomics. From my point of view, it's really amazingly simple and elegant theory which allowed people to understand the effect of activation by itself. So changing in the population of these two molecular orbitals leads to the activation of the coordinated carbon monoxide in this case, or any AB diatomic in general. Now, it was shown that a population of this pi orbital strongly affects the strength of the CO bond. However, population in the sigma bond, because it's non-bonded, slightly affected. Here you can see the process of coordination, where there is some metal center with carbon monoxide. This is sigma bonds, and this is interaction with pi bond. So here there is charge transfer from metal to the empty pi bond, empty pi molecular orbiter of carbon monoxide. Here you can see it in details, and this is what is called pi band bonding, charge transfer from the metal to the carbon monoxide or any other ligand. Now, using the Bersuker's approach, we have calculated effects of different charges located around the heme complex with carbon monoxide on the frequency of the carbon monoxide. This is carbon monoxide, different charges around. And we obtained that how it was expected, the major contribution to the activation of the carbon monoxide, in particular in change of the frequency of the carbon monoxide frequency, stems from the electron density transfer to the 2 pi orbital of the carbon monoxide. Here you see the correlation for all the cases studied by us. So this was a start, and then we moved to study myoglobin with carbon monoxide, which was published And now I want to talk about horseradish peroxidase. Horseradish peroxidase is a real enzyme which activates peroxide, and its mechanism you can see at this scheme. Here you can see the protein. This is heme. This is histidine, which is coordinated is bonded to the protein. Here there is environment of the heme. Here in details you can see the environment. So this is heme, carbon monoxide, imidazole of the histidine. This is aspartic acid, of course, model of aspartic acid. This is distal histidine, and this is arginine. Now, if you look at this picture, you see actually a capacitor. Indeed, aspartic acid is negative, arginine is positive. So there is electric field directed from minus here to plus here. And of course, this field is expected to affect electron density transfer from iron, or actually from the iron porphyrin, to the carbon monoxide. It's interesting, this imidazole, this histidine or imidazole in our case as a model, it can change its protonation. At low pH, it's protonated, double protonated, or fully protonated. In the neutral case, at high pH, it's only one proton exists, is bonded to the nitrogen of the distal histidine. So we were interested to study how these environments affect the carbon monoxide properties. And this is actually, there is a more general problem here. It's very well known that heme is an active center of very different proteins which perform very different actions. And all these differences stem from the different environment. So here's a result of our calculations. We used already the direct quantum chemical calculations. And you can see that indeed the addition of different charged amino acids strongly affect the CO frequency, or in other words, strength of the CO bond. This is pure heme CO, and this is what we have if we have heme plus aspartic acid only. This is if we have imidazole, histidine, distal histidine with hydrogen, with proton on different imidazoles. This is the full structure, no arginine, the same story, delta and epsilon protons, no water, and this is no imidazole. In this case, we have fully protonated imidazole, which exists at low pH. So you can see that indeed the environment can and should strongly affect the vibrational properties of the CO, and consequently it activates the carbon monoxide. Now, in the case, for example, of myoglobin CO, there are no such polar or charged amino acids around, and therefore in myoglobin and also in hemoglobin, the protein keeps dioxygen intact and just allows to move it from one part of any organism to another part. In this case, there are charged amino acids which can activate any coordinated ligand. Now, I would like to stress the CO here is only a probe, but in principle, if we have another ligands, it will be the same, because the pi-back bonding exists in any case, and transfer of electron density will take place in any case. And therefore, the CO activation is just a zone which allows us to conclude how active can be this or another protein to activate any diatomic ligand which is coordinated by the heme. In other words, what we can say that this surrounding strongly reduces redox potential of the heme and of the whole protein. So it can really inform us about the activity, the activity of this protein as monooxygenate. This is the end of my scientific contribution, but I would like to complete with wishing Professor Bersuker, like they say in Hebrew, ad mea v'esrim kmo esrim, which means in translation, till 120 like 20. So be healthy and wealthy. That's it.
Thank you. Thank you.
Thank you, Professor. Any questions from our small room or from wait, thank you so much. Thank you so much. Professor Stavrov. I invite Garcia Fernandez. Are you online?
Yes, yes, I am.
Jahn-Teller and pseudo-Jahn-Teller effects in excited states.
Okay, can you see my screen?
Please.
No. Okay.
Yes, I see you.
Okay, no, my screen. Okay, that's it. Okay, please. So good afternoon, everyone. First of all, of course, I would like to thank the organizers and, of course, Isaac for considering me to participate in this fantastic occasion. So what I want to tell you today is a little review of the work I carried out in the in Professor Bersuker's group in Austin between 2005 and 2007. So when I arrived there, the group was composed by the two senior scientists, so Professor Box and Professor Bersuker, and Alexander Marenik, who was a postdoc at the time in the group. So for me, coming from Spain, it was a very hectic time, and I was very, very happy of the results we obtained. So the idea for the project was to test essentially Jahn-Teller. So the first part of my project included trying to check whether Jahn-Teller work in soft molecules And this was interesting because Jahn-Teller is essentially a perturbative approach. So it works better when the perturbations are small, and the perturbations here are associated with the distortions. One of the things that we wanted to check is, okay, what happens if our molecules present large distortions? So in order to test it, what we did is we carried out simulations in soft molecules that, of course, the moment they present byronic coupling, they present large distortions. And so we expected to test the theory outside the comfort zone of the usual perturbation theory. And another interest that I had at the moment was related with a previous work of the group in around 2000 with Professor Koizumi, where they discuss the possibility of complicated energy surfaces associated with a very strong quadratic coupling, which then presented several conical intersections. So this publication in Physical Review Letters was purely theoretical in the sense that it didn't have systems or calculations in particular systems where this could appear. So one of the goals was to trying to get to find systems that presented these very particular energy surfaces. So at the moment, it was not clear to us, but what we found is that the solution of one of the problems, or at least the investigation in one of the problems, led us to the solution of the other. So let me start with the soft clusters. So the idea is, or the idea at the moment was to test what happened with first principle simulations with second row tetratomic clusters, sodium, magnesium, aluminum, phosphorus, sulfur. What we knew at the moment is that there were reported geometries of each of these clusters. They were very different. Some of them were had a rhombus shape, other pyramidal, and others were trapezial. They had the shape of a trapezium. So one of the things we wanted to do is we wanted to explain these very different geometries with Jahn-Teller and pseudo-Jahn-Teller theory, and observe what happened with the theory when we tried to apply it to very large distortions. So the theory worked beautifully in all of them, even with very, very large distortion, as here with 0.8 angstrom distortions. And so this was a very, very successful story for pseudo-Jahn-Teller. But we found another thing that immediately called our attention, and that was that in many of the system, the global minimum of the molecule didn't come from the global minimum at the high symmetry point. What happened, in fact, is that the Jahn-Teller and the pseudo-Jahn-Teller effect occurred in the excited state, and then there was a crossing that produced the global minimum. Okay, so immediately Isaac proposed to call this the hidden Jahn-Teller effect. So the idea was that you could have a system where your ground state was non-degenerate, but an excited state, like an excited E state, produced the Jahn-Teller crossing with the initial ground state to give the global minimum. So it was very clear that this could have influence in the dynamic of many molecules, because the Jahn-Teller effect carries other phenomena like the very phase. And so this could influence many properties. And not only we proposed that, but we, of course, found systems where this happened. So here you can see first principal simulations of the ozone molecule, and you can see how the Jahn-Teller in the E excited state comes down and becomes the ground state. And the stabilization energy in this system is huge. It's larger than 12 electron volts. So this meant that the dynamics in the ground state associated with the ozone molecule was, of course, affected by the periphase. And this was quite important for us at the moment. Secondly, we also found a number of systems that were based, well, first in the small clusters, but that had a very particular electronic configuration that was a half-filled degenerate cell, so an E2 or a T3 electronic configuration. And we found that there was a pattern in this kind of configuration that produced the many conical intersection picture that we found that Professor Bersuker and Professor Koizumi found in their 2000 paper. So here, for example, we can see one of those examples in an E2 molecule where, in fact, the ground state is a triplet, and it's not active vibronically, but on the other hand, the excited states are low spin, and in this low spin, you can see that here there is this blue curve and this green curve, and they produce several crossings here very close to the initial conical intersection. Not only that, but this E excited state is strongly coupled to the A1 excited state, and that produces a very strong stabilization that crosses with the ground state and produces the global ground state of the molecule, which is this distorted singlet. So I remember perfectly well when I showed this picture to Professor Bersuker. And he immediately realized the importance of the physics in this system. He immediately saw that there was a triplet state that had one geometry. There was a singlet state that had another geometry, and that these two states competed in energy. So this was very similar to what happened in spin crossover systems in transition metals, and we called this phenomenon in these molecules the vibronic spin crossover. But I want to stress the real quickness in which Professor Bersuker realized the importance of these systems. So after that, we expanded this concept into because this vibronic spin crossover was not just associated with spin. There were other phenomena or effects that could be triggered. For example, the two states could display a different polarization. So you could have a simultaneous change in spin and polarization. And this was not just restricted to molecules. We applied it also to solids. And we also studied the lifetime to move from one configuration to another. And in fact, we saw that in certain cases, the lifetime of the metastable state was quite high, macroscopic. So this could, we proposed that this could be a nice way of developing new, for example, multiferroids or other nanomaterials. And these discoveries had also important repercussion in order to understand very basic chemical properties. For example, how molecules could rotate along a double bond. And these double bonds are usually found in many nano machines, molecular machines. So here I showed you ethylene, so a very basic molecule with a double bond in the D2D geometry. So the moment you plot the molecular diagram for this molecule, you can see that the highest occupied molecular orbital is a half occupied degenerate state. So this is an E2, so it is a spin crossover system, and the prediction is that there is a triplet ground state for this D2D configuration, and then we have a very strong pseudo Jahn-Teller that lowers a singlet, and that is exactly what happens. So this the stabilization of this singlet, what it's doing is really creating the double bond. So something so fundamental to chemistry like a double bond can be easily explained through the pseudo Jahn-Teller effect. And this mechanism works similarly in many other linear double bonds. For example, in azobensin, which is a molecule usually employed trying to work out how to create molecular switches. So the energy surfaces of this molecule that are usually activated with photochemistry are very complicated, but using this simple idea of the E2 configuration and the states that arise from there, we were able to explain all the different configuration of this molecule, and we were able to rationalize this complex system. This also provides you with tools to understand and manipulate the chemistry of many systems. So just as a summary, I would like to stress how Jahn-Teller and pseudo Jahn-Teller effects underpin many fundamental processes in chemistry. And of course, the ideas of Professor Bersuker have enormously contributed to the understanding of many of these properties. And just to finish, I just want to say that I'm proud to have played a small role in these developments, collaborating with Professor Bersuker, and I would like to wish Isaac a very, very, very happy birthday.
Thank you.
Yes, thank you. Any questions inside of our small room of Academy of Science or online, from online, please? Colleagues? Not? Thank you,
Okay, thank you.
Garcia Fernandez. I give the floor to Adel Kiev. Jahn-Teller effect in semiconductors. Please. Are you online?
Yes, yes, thank you.
Please.
Thank you very much.
Welcome.
First of all, I would like to participate in the seminar and congratulate Professor Bersuker. Just a minute.
Thank you.
Okay. Do you see my screen? Okay, sorry. Do you see my screen?
Yes, yes, we see.
Okay, thank you. I would like to say about effect Jahn-Teller in semiconductor. The plan of my report is present here. First, I say several words about deep level in semiconductor, and then speak about defect in cubic symmetry semiconductor and with different symmetry of defect, and conclusion. My report is based on 3 works. 2 of this was made with Professor Bersuker, And the third is my work with my colleague. Some words as introduction. In semiconductor, there are two types of impurities that give a level in the band gap. See this as scheme. Conduction band, valence band, and the level of the defects. As I mentioned, there are two large groups of the defects. Shallow impurities and deep impurities. Deep impurities means that the binding energy is approximately the band gap. And for the shallow impurity, the binding energy is more or less than band gap. And the main point is that the radius of the wave function in any case may be estimated as I wrote. It means that for the very deep center, the radius of wave function is approximately as a lattice period. And for the shallow primitive impurities, this radius is more large than A. But there is an immediate case when binding energy less than deep or more than shallow impurities. It means that the corresponding radius is approximately 2,5A. In this case, I may consider the impurity atom plus lattice atom nearest to the impurities as a molecule. And the wave function of the charge located in that center will cover only nearest atom. And I may consider this complex as a single molecular. And the first example is the very popular impurities kappa in gallium arsenide. Kappa belongs to the first periodic table. For this reason, in the neutral state, this center may capture two holes. As I mentioned, the binding energy is approximately 100.5 MeV, and the radius approximately 10 angstrom. It means 5A, small a. As I mentioned, I may consider this complex as a molecule in the center kappa and around 4 atoms of arsenicum. Since the top of the valence band in gallium arsenide has the symmetry as gamma 8, and I have 2 holes, it means that I went to the gamma 8 task, and I would like to demonstrate the very famous picture, the adiabatic potential, which correspond to this complex in 2 situations. in natal state and after optical transition. We would like consider the initial state before optical transition. Since we have two whole, and we have to consider the corresponding Hamiltonian. The Hamiltonian contains 6 states for two whole, since we have to take into account Pauli principle and interaction with oscillation. Okay, this is a section of adiabatical potential, and the main question which were raised before us, how to estimate or measurement the transition between equivalent position. There is a barrier between position and the problem how to calculate or estimate or measure this transition. Theoretically, we estimate the time of transition, but our colleagues, experimentators, study the ultrasonic adsorption of this crystal, since we may excite ultrasonic wave with different orientation k vector and vector of deformation, and it's not very complicated to consider different situation with a fast wave and slow wave, and we may obtain that there is a strong adsorption for slow wave and there is no absorption for fast wave, and this is a reason only symmetrical, since the fast share wave did not change the equivalent between minima, and slow wave change the equivalent of the minima. And you can see that there is a temperature dependence of the orientation time. At low temperature, we have characteristic curves, which means there is a tunneling process. We may estimate this time, and our estimation was very good agreement with measurement time. The next example, the chromium center in A2,6B6 compound. Here we have to take into account the number of electrons which occupied the one electron states, and in results we go to the T2 type symmetry state in cubic crystal. In that situation, we have TE problem, and as you know well, Here we have again 3 minima of adiabatical potential, but there is no transition between extremuma. Again, if we start experimentally study of adsorption ultrasonic, we obtain the strong adsorption, but in external magnetic field. Really, to explain this experimental facts, we have to consider the role of magnetic field. And indeed, if we include in the Hamiltonian the magnetic field, we see that there is a transition between the state of the minimum of adiabatic potential. We calculate the corresponding time. The time is proportional to the magnetic field but in power 2. And again, we may both estimate and measurement, and we have a good agreement between this number. And the final example is a rather complex vacancy, complex in gallium arsenide again. Here a picture of this complex at the beginning of our study. We have impurity, here tellurium, substitution arsenide, and there is a vacancy. Since there is initially the complex has C3V symmetry, not a cubic symmetry. Experimental data for this complex was obtained due for optical experiments, and we made 2 types of experimental study. Under external stress along different crystallographic axes and resonance polarization spectroscopy, when we illuminate the crystal on one axis and with the angle polarization between angle and E field, and the observed direction. Using this method, we may obtain the symmetry of the defect. And the result of the experimental study, here the difference of the polarization ratio of the photoluminescence from this defect with different external loads. From this for the direction 1 direction, and here for 0, 0, 1. There is a strong differences. For instance, for low temperature, curves 1 corresponds to T2 degree. This strong anisotropy gives us possibility to consider that we have the center with trigonal axis. But study different method. It's not easy explain, but I ask you to trust me that if the center was trigonal symmetry, this curve gives zero signal, but there is a significant degree of polarization. It means that we have the symmetry plane, and the symmetry of the center is C2V, and of course for concrete example, vacancy and the impurity, we have three different situations when this plane may be as shown in picture, and another two possibilities. For instance, from this diagonal and from this and the next. And again, we would like to explain the existence of such center and the possibility to transition between equivalent minima using the Jahn-Teller effect. As was mentioned, this is a symmetry. This initial symmetry is C3V, and we have to consider again interaction with E type of oscillation. But here you can see we have not only the Jahn-Teller effect, but as well pseudo-Jahn-Teller effect. We take into account the different number of electrons occupied in excited state, and the excited state, it means in radiate state, and we can understand how the Jahn-Teller effect acts in Z station, adsorption state, and in radiant station. Okay, thus I would like to give a short conclusion.
Sir?
Yes, and I'd like to say and congratulate our Professor Bersuker again, and glory to our jubilar. Thank you for your attention.
Very good wishes. Any questions, please?
I have a question.
Please, Professor Academician, Professor Saborisic.
Yes, Nikit Sergeyev, who made the optical experiments on gallium arsenicum?
There is a group in our institute headed by Professor Gutkin.
I see. Have they made the other experiments with Jahn-Teller centers?
I told about optical experiment, which demonstrates the role of Jahn-Teller effect. Of course, there is a very extended area to study the Jahn-Teller effect using EPR study, of course.
I see. Okay.
Moreover, in our common study, we use the result of EPR study.
I see.
Okay. Other questions online? In our room? No. I want to ask Nikita Sergeyevich, yes?
Yes, yes.
Kiev. Physical Technical Institute is from St. Petersburg. Is the Institute of Russian Academy of Science?
Russian Academy of Science.
Russian Academy of Science. Thank you so much.
Yes.
If not other questions, I want to say Professor Hiro Kuzmini, good night. 2:40 a.m. I invite, give the word to Professor Hiro Koizumi, is Tsukuba University of Japan. Jahn-Teller effects, very fast and superconductivity. Please.
Please, okay.
Well,
Okay.
but is night or is day in Japan now?
Oh, it's night. It's night, early in the morning.
Please.
Can you hear me?
Yes, you hear you.
Yes.
Okay, and so I'm glad to see Isaac is very still energetic and very enthusiastic for research, and I was very honored to work with him on Jahn-Teller works, and I'm going to talk about the work I did with Isaac, and also something new I'm doing right now. And okay, we start from here and the slideshow. Wait, maybe we should, this one. Okay. So this is the right one, right? Okay. And actually, so what I did long time ago with Isaac is this E cross E program of this Jahn-Teller program. At that time, this E cross E program potential surface are just one conical intersection at the centers. But if actually Pablo already said, if the quadratic interaction is very large, then we have three extra conical intersections appears, and then the symmetry of the ground state changes, and this is actually due to the very phase effect. So at that time, somehow very phase was beginning to very popular in physics, and we actually found a very solid example of how very phase affect the physical systems, and so we find that this very phase is very important when we consider physical systems. And also this is Michael Berry. I took picture at the Jahn-Teller conference at the Santander, and then this paper appeared in 1986. And this is actually what Pablo already showed. And this we have three. Ordinarily, there is only one conical intersection here, but if we have a large quadratic coupling, we have extra another three conical intersections, and then this E ground state and A ground state changes with change the parameters. That's actually what we did, and which is we calculate tunneling probability here, and we identified that this change is due to the very phase appearing in those conical intersections. Okay, and actually this is not actually the beginning. Actually, I'm interested in this, what this very phase really is, and I did some kind of wave packet propagation with a system with conical intersections. And in that case, what I observed is we start from a wave packet here, and the time is proceed in this way. In this case, if a Berry phase does not exist, this wave packet goes around conical intersections, but with constructive interference at the other side of the conical intersection. However, if this conical intersection and Berry phase effect is included, we have this destructive interaction, interference at the other side of this potential surface with conical intersections. And this actually really haunted me in a sense. This is not just the change of the interference patterns, but also means that it seems even a ground state, there is some kind of non-trivial moving motion exists in this system. It's basically a dynamically antenna effect, but in this case, it is caused because due to this Berry's work, we can now consider this phenomena as a consequence of this Berry phase. And this kind of, this may be seen as we have a phase pi change. The interference change from here to here is a phase pi change due to the Berry phase. And there's another phenomenon which seen is in this kind of pi phase change is found in an experiment by observation of a Harlan-Bohm effect in superconductors. And this is an experiment which done by a Japanese researchers at the Hitachi laboratory, headed by Tonomura. And they used this kind of toroidal magnet, which magnet is this permalloy. Permalloy has this toroidal shape, which is covered by a niobium. Niobium is a superconductor. So if the temperature is low enough, this niobium becomes superconductor. And if this niobium becomes superconductor, the magnetic field arising from this permalloy is covered. It is confined. The magnetic field does not come out of this superconducting niobium. So in this case, we can shield magnetic field from permalloy if niobium is in a superconducting state. And the experiment, what they did is a Harlan-Bohm effect, which sees the effect of vector potential. Even magnetic field does not exist. The electron should feel the vector potential and change the interference pattern of this electron beam. This is what they did with this experiment. And what they found is, and so temperature is 4.5 K. At this temperature, this niobium is in superconducting state. And we have A, this is temperature is 4.5, this is superconducting, and B is also superconducting, and C is not superconducting. So if this at above superconducting temperatures, this interference pattern is something between 0 and pi, which because the permalloy emit magnetic field, and because of this magnetic field, the electron coming in this the center of this toroid and the outside of toroid make some interference, but which is not the phase change is not 0 or pi, somewhere between them. But if it is superconducting, the phase change is 0 or pi. Okay, so 0 or pi. So we see some kind of pi phase change from here. So in this case, this superconducting phenomena may be considered as due to some kind of vector potential, which causes this pi phase change. And it seems like this is very similar to what we observed in the wave packet motion around conical intersections. Okay, and then another at the time around 1986, Mueller found superconductivity in cuprates. And Mueller is led by the Jahn-Teller effect. He thought that because of this Jahn-Teller effect will provide very strong electron phonon interaction, and which will create a very high, create Cooper pairs at very high temperatures, and that will give you the very high superconducting transition temperature. And that was his motivation. And actually, he found led by this Jahn-Teller bipolar mechanism to for this superconductivity. But is this really this idea, Jahn-Teller bipolar as Cooper pairs, is this really right idea for this cuplet superconductivity? That's actually really and my question. And also, what is actually even now the cuplet superconductivity is not solved in a sense that no widely accepted theory exists for this mechanism, this superconductivity. But it is true that the Jahn-Teller small polarons are observed in this material. That is true. So strong electron phonon coupling by Jahn-Teller effect or through Jahn-Teller effect exists in this system. But relation between this and superconductivity may not be the one envisaged by Mueller. And the interesting thing is, this is actually really seen here, is this cuplet superconductors, and this gives some kind of ratio, which gives the ratio of observed TC and this TC max. TC max is something corresponding to the stabilization temperature for coherence length size loop currents. And cuplet case, this coherent length, superconducting coherence length is in the order of nanometers. It's basically a couple lattice constant of CO2 plane. So it seems like a cuprates this TC superconducting transition temperature coming from stabilization temperature of nanosized loop currents, not from the electron pairing energy gap formation temperature. Actually, standard theory of superconductivity, superconducting transition temperature corresponds to the electron pairing energy gap formation temperature, but cuprate, it is not. So this actually really deviates from the standard theory of superconductivity. And what really seems to be important is to identify what is this nanosized loop current, and which is not really verified, but there are several experimental results which indicate the existence of nanosized loop currents, which is different from Abrikosov vortex. Abrikosov vortex is also loop current, but which is much larger than this nanosized loop current. But cuprates show some signs of existence of nanosized loop currents. And actually, I've been working on the theory which this nanosized loop current is created around a small polaron hole. Hole makes small polarons and makes a spin vortices around it and makes a loop current, which is this because the spin vortices create Berry phase. So in this case, Berry phase is the origin of this loop current, and which seems to be related to the superconductivity in cuprate. That's actually my theory of cuprate superconductivity, but this loop current has not been observed yet. This, but now probably we are trying to observe somehow this single loop current, which probably now experimental methods have been improved. So there will be methods to really detect this single nanosized loop current. And actually we are thinking about how to detect this one. And then what really happened is, if you really think about this cuprate superconductivity, this cuprate superconductivity seems to be really depart from the standard BCS type superconducting theory. But actually, if you really measure many properties of superconducting states, like flux quantizations or AC Josephson effect, actually those are the same. So seem to be like we need a superconducting theory which explains both cuprate superconductivity and BCS superconductivity from a more fundamental level of theory than the BCS theory. And actually, BCS theory is very successful in a sense that it explains how to calculate superconducting transition temperatures for some materials. But actually, if you really close to look at it, actually BCS theory has some problems. Actually, there are, and now seems to be that the BCS theory, there can be a superconducting theory for superconductivity, which can explain the standard superconducting theory and also Q-plus superconducting theory on an equal footing if you really use this very phase as a motive force behind the superconducting current. And what really happened to seems that it seems that our Schrödinger equation, we are solving a Schrödinger equation as a fundamental equation for the materials, but actually Schrödinger equation has neglected U1 phase, some U1 phase, which I'd like to explain. And in the Schrödinger equation, we use a coordinate and momentum. This momentum is conjugate to variable, canonical conjugate to this coordinate, and which we usually use as this differential operators. This is actually Schrödinger adopted this relation, and we usually use this relations. But what is more fundamental is not this relation, but this Heisenberg's commutation relation. This relation is more fundamental than this relation. In that case, we may use this PR, this differential operator. Instead of this differential operator, we could use this differential operator with additional term here. But Dirac said that this extra term can be absorbed as a U1 phase in wave function. So we usually, we can always use this momentum use this, and but in this case wave function becomes this. But if we calculate this whole wave function as a unit, then we don't have to worry about this e to the I gamma. We just obtain this whole thing together. But this very phase problem indicates, no, we cannot ignore this one. The reason we cannot ignore this is this phase factor may be multi-valued, and this phase factor contains some kind of singularities in this some coordinate point. For example, at the point of conical intersections, or in this spin vortices case, at the center of spin vortices, we have some singularities, and if we have those singularities, we really have to include the existence of those singularities, and which cannot be. If those singularities exist, we cannot solve this wave function as a whole. We have to really think about what this means and what this causes the dynamics. And if we think this as a very phase and do some manipulations, we come up with a very almost all exactly the same mathematical type of superconducting wave function as the BCS wave function does. But in this case, this phase factor, which appears in the BCS theory, becomes something related to the very phase. And so this theory is actually really complicated. So I'd like to just state what I found from this way of including Berry phase in a superconducting state is that anyway, it's this theory will basically capture the almost all the experimentally verified result of BCF theory. So this theory will explain all the goodies of the BCF theory. And in addition to it, this theory has two very gratifying differences. What the one is, the ground state is particle number conserving. That means the BCF theory uses a particle number non-conserving formalism to take into account the pairing formation. But actually, if we start with this Berry phase formalism, this pairing stabilization of the BCF superconducting state by electron pairing occurs, but which is not really the essential part of the superconductivity. Essential part of the superconductivity is this phase, the collective mode created by this mode, which is a superconducting current, and which is stabilized by the electron pair formation. So BCF theory really explains this how this current formation is stabilized. So that's the reason this theory and the BCF theory have the almost all good experimentally verified result. And another point is there is a phenomenon of London moment in superconductivity. The London moment is if superconductor is rotated without applying magnetic field. Okay, so if superconductor is rotated, magnetic field appears inside the superconductor, and which causes a magnetic moment, and this magnetic moment is called the London moment. And if you measure this London moment, you can obtain the mass of this supercurrent carrier. And actually, strangely enough, from the viewpoint of the standard BCF theory, this mass is always free electron mass, and which disagrees with actually BCF theory. In the BCF theory, this mass should be an effective mass of a metallic state. But experiment always have obtained this free electron mass. But in this Berry phase supercurrent theory, we get this free electron mass all the time, because this Berry phase act as a vector potential, like a electromagnetic vector potential for electrons. So the mass for this vector potential acting is always free electron mass. So if you instead taking this part as a Berry phase, and also some other part may be changed a little bit, but this formalism will capture all the goodies of the BCF theory and change the formalism to a particle number conserving one, and also it gives a free electron mass for the London moment. And it seems like this new theory is more which attributes the origin of supercurrent to Berry phase is more elegant and more agreeable with experiments. And this is my talk. And so lastly, I like to say Isaac for the so I hope thank you for inviting me to speak this very good opportunities. Also, I think Isaac can continue his research enthusiastically for a long time.
Thank you.
Thank you, Professor Hiro Koizumi, for very interesting discussion around superconductivity. Questions?
No.
Only two.
Online?
Only
No.
2 words. Very nice.
Very nice. No, nice.
Very.
Thank you, Doctor.
Thank you very much. Thank you very much.
From Romanian Academy of Science. Okay. We finish our webinar, and I want to ask you if you intend to participate in the discussion. Some opinion, please, inside in our small room or online. I invite who want to talk about our webinar. It's okay. Maybe academician Bersuker or no.
Yes.
Gero, just a moment. Ion Gero.
Yes. Dear Academician Bersuker, Professor Pollinger presented today your lifeline, including the period when the Institute of Chemistry was organized in the Moldovan branch of the All-Union Academy of Science. As a beginning researcher of this institute, I had a possibility to know you as a young doctor of science, full of energy and ideas. It is known that one of my concepts of the theory of symmetry is the conception of invariance. You proved that your extended scientific interests are invariant during the time. Let me to wish you the health and success during a long time. Thank you.
Thank you.
Thank you, member of Academy of Science of Moldova, Ion Gero. He worked many times in the laboratory of physical and quantum chemistry. And other, maybe Isaac Borisovich, you.
Yes.
Please.
Yeah. First of all, I should like to thank the contributors, the speakers today. I am impressed, and I appreciate very much their contribution, both scientific, and congratulated me. And what I want to tell them is not to forget to present their papers for publication in our Moldovan journal. So we will have all of them together, and will be a volume which is devoted to this point. And also, I would like to thank my Moldovan colleagues. This is my place. I am Moldovan, so I am very glad and happy that they organized this webinar. Again, I hope to do it again in 5 years. I will be 100 years old. Yes. to all the people who maybe listen today, and to our participants and to our speakers, I should like to remind us that we have the 25th International Conference on the Jahn-Teller effect, which will be in May. And I asked them to register, and we succeeded to make this conference this time without any registration fees. And it's a long time we had this interruption of the conferences, so we hope that we will get again, maybe it's a webinar, but still we'll get again and we'll discuss the Jahn-Teller effect. Again, thanks to our organizers, to academician George Duca, to the president Ion Tighineanu, to the director of the Institute of Chemistry, Acolina Rico. Thank you, and I hope to continue, and we continue to work together on the projects which the Institute has now in work. Thanks.
Thank you so much, Isaac Borisovich. It's very interesting webinar. Today we organized together because I think this webinar transformed in one international conference of Jahn-Teller effects, which 9 plenary sessions, 9 plenary presentations. It's very interesting. It is a very high level of the presentation, and I thank so much. And we understand. I thank again all speakers and for great presentation. And I want to say. I want to say many directions open your research in Jahn-Teller effects, and 6 or 7 directions we listen here now in this webinar. I want to thank, like you, Isaac Borisovich, first of all, laboratory of physical and quantum chemistry, Jolanta, director of the chief of this laboratory, Jolanta Balan, Natalia Gorenchoy. I want to thank the Institute, director, Acolina Rico, vice director, Raisa Anastas. I want to thank Academy of Science, president, academician Tighineanu, vice president Svetlana, member Academy of Science Svetlana Kozhukaro, and the secretary of our section, next member of Academy of Science, Georgi Ursaki, help us very well. Academy of Science and Institute and all persons who participate. One conclusion for me, very important, is the research in the Jahn-Teller effect. Your research, Isaac Bersuker, and the people who presented the allocation changed the perception of the world and contributed to the development of optical, electrical, quantum, and other technologies. The last person, Hiro Kozumi, give us a very good example about the role of Jahn-Teller effect in the conductivity. And last, I want to congratulate again Isaac Borisovich for this 95th anniversary. It's very interesting, it's very good. You look very young. I try to explain with the electron and positron, with the quantum different effects, and I think it's very good activity, very good life, and I wish to organize the next seminar after 5 years, when will be 100th anniversary of your birthday.
Thank you.
You are very young. You are very good. You are very strong. You are. We wish you many health.
Thank you very much. Thanks a lot.
Thank you for you, and thank you all who participate of this seminar. Goodbye, good night, good day, good night for us, a good day for Japanese and Chinese, and a good afternoon for you, Isaac Borisovich.
Thank you very much.
La mulțani, Isaac Borisovich, la mulțani.
Mulțumesc din inima. Mulțumesc.
Dumneavoastră meritați. Vă mulțumim foarte mult pentru că dumneavoastră ați umplut inimile noastre cu multă știință, informație și speranță. La mulți ani dumneavoastră. Vă pupăm, vă îmbrățișăm, vă iubim și dorim ca peste 5 ani să ne întâlnim tot în această sală, tot cu acești oameni, poate mai tineri, și să vă felicităm și să facem acest seminar. La mulți ani. Mulțumim foarte mult. Ideea a fost minunată. Astăzi, la noi, în Academia de Științe a Moldovei și în Institutul de Chimie, a fost o lume întreagă științifică. Vă mulțumim dumneavoastră. Lumea care a fost pregătită de dumneavoastră, personal. Lumea care a mers pe calea pe care ați arătat-o dumneavoastră. La mulți ani.
Thank you very much. Thanks a lot. That's very impressive. And I am thankful to my Moldovan colleagues, all of them. It's my birthday, birthday today, but it is my birthplace, Chișinău of Moldova. In my place of my science.
Might be in the end is necessary, like Moldavian tradition, to drink not water, not coffee, wine or cognac.
We'll do it maybe later.
Thank you so much.
Thanks.